Welcome back to Supernova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. We look up on a clear night and see thousands of tiny lights sprinkled across the sky. From ancient times to the present, people have been captivated by the stars. They have inspired wonder, guided travelers, and sparked countless myths and legends. Humans imagined patterns in them and told stories about gods, heroes, and animals in the heavens. We use the stars to navigate oceans and to mark the seasons. But what are these brilliant pinpricks of light really? Stars are giant, luminous balls of plasma held together by their own gravity and powered by nuclear fusion at their cores. In simple terms, a star is a colossal nuclear furnace in space, constantly fusing lighter elements into heavier ones and releasing tremendous energy as light and heat. They seem eternal and unchanging to us, but in reality, stars are born, they age, and they die, undergoing dramatic changes over millions or billions of years. Our Sun is one such star. In fact, it's the only star close enough for us to feel its warmth and light directly. And it's just one among an uncountable multitude of stars in the universe, each with its own story. Now, imagine journeying into a vast cosmic cloud far out in space, where new stars are born. These regions are called nebulae, enormous, diffuse nurseries of gas and dust, sprinkled throughout the galaxies. They are the cradles of star formation. If you could float inside one, you might see faint, ghostly glows and dark, opaque patches where starlight from outside is blocked. The famous pillars of creation. Photograph of the Eagle Nebula, for instance, shows towering columns of gas and dust rising like mountainous spires. Within those cold, shadowy pillars, new stars are slowly taking shape. The Great Orion Nebula, visible as a faint smudge in Orion's sword, is one such stellar nursery. A cavern of gas and dust over 20 light-years wide, where thousands of baby stars are forming. Here, in the cold, dark depths of a nebula, the story of a star begins. A slight nudge, perhaps the shockwave from a distant supernova or a random density fluctuation, causes parts of the cloud to begin collapsing under their own gravity. Over thousands to millions of years, a portion of the nebula's gas gathers more and more mass, pulling in surrounding material. As this pocket of gas shrinks, it grows denser and hotter, and it starts to spin faster. Eventually, it forms a growing ball of gas known as a protostar, a baby star that's still gathering mass. Surrounding it, a flat disk of gas and dust often forms, whirling around the protostar. Protostars also often fire out bipolar jets, narrow beams of gas blasting out from their north and south poles. These high-speed jets can plow through the surrounding nebula, creating glowing shockwaves and carving cavities in the cloud. The protostar at the center continues to contract and heat up as gravity relentlessly squeezes it. Deep in the core of this protostar, temperatures climb into the millions of degrees. The gas is mostly hydrogen, the simplest and lightest element. When the core temperature reaches roughly 15 million degrees Celsius, something miraculous happens. Ignition. Hydrogen nuclei begin to fuse together to form helium, unleashing a tremendous amount of energy. This is the moment a star is truly born. The protostar has become a full-fledged star, blazing with its own light. The once dark core suddenly glows brilliantly, and the outward pressure of this new energy release halts the gas collapse. The infant star turns on, so to speak, and starts shining. The surrounding cocoon of leftover gas and dust gets blown away by the fierce stellar winds and radiation now pouring from the newborn star. The star stabilizes, no longer contracting, as a balance is struck. It has entered the long, stable phase of its life, known as the main sequence. Often, stars do not form alone. Many newborn stars come in groups called star clusters. Our Sun likely formed in a cluster with several sibling stars. which have since drifted away. Once nuclear fusion starts in the core, a star finds an equilibrium. Outward pressure from the fusion energy balances the inward pull of gravity, and the star stops shrinking. It becomes stable, neither collapsing nor exploding, steadily glowing. The star will remain in this state, fusing hydrogen in its core for the vast majority of its lifetime. It's as if the stellar engine is idling at a steady rate. This newfound stability allows the star to shine consistently for a very long time. Millions, even billions of years will pass with the star in this tranquil main sequence phase. Our Sun is in fact in this phase right now and has been for about 4.6 billion years. This stability is fortunate for us. It means the Sun's energy has been steady enough to allow life to develop on Earth and will continue for eons more. If our Sun were a short-lived massive star, life as we know it might never have had the chance to arise in the brief stellar lifetime. Main, sequence stars like the Sun quietly convert hydrogen to helium, radiating energy into space and providing warmth and light to any orbiting planets. In this main sequence stage, a star shines by nuclear fusion, fusing hydrogen atoms into helium in its core, and in doing so, it releases an absolutely colossal amount of energy. To give a sense of scale, our Sun fuses about 600 million tons of hydrogen every second, turning it into about 596 million tons of helium. The missing mass, roughly 4 million tons per second, is converted to pure energy according to Einstein's famous equation E=mc2. 4 million tons of matter turned into energy every single second. This energy then radiates outward from the core, through the Sun's layers, and eventually into space as heat and light. The numbers are mind-boggling. The Sun's energy output each second is about 3.8 × 10^26 watts, a figure almost impossible to imagine. To put it in human terms, the power the Sun releases every second is equivalent to the energy from billions of nuclear bombs exploding at once. Yet this gargantuan output has been running continuously for billions of years, and will continue for billions more. It's sobering to realize that for most of human history, the source of the Sun's power was a mystery. Only in the 20th century did scientists like Arthur Eddington and Hans Bethe figure out that nuclear fusion is what makes the stars shine. Millions of such stars fill our galaxy, each a massive energy source blazing in space. Not all stars are like our Sun, however. Stars come in a stunning variety of sizes, colors, and luminosities. Some are far bigger and hotter than the Sun, shining blue, white, and piercingly bright. Others are smaller and cooler, glowing a faint red. The color of a star is a clue to its surface temperature. Hotter stars emit more blue, white light. Cooler stars more red, orange light. For example, in the constellation Orion, you can spot a contrast between the supergiant star Betelgeuse, which shines with a reddish hue, and Rigel, which gleams bluish-white. In general, a blue star might be tens of thousands of degrees at its surface, while a red star might be only a few thousand degrees. These differences correspond to spectral classes. Another example, the star Sirius, the brightest star in Earth's night sky, is about twice the Sun's mass and has a surface temperature of around 9,400 K, giving it a white-blue sparkle. On the other hand, our Sun is yellow, white, and a typical small red dwarf star would look deep red to our eyes. The vast majority of stars in our galaxy are actually small, cool red dwarfs. Perhaps 70–80% of all stars fall into this category. These red dwarfs are so dim that not a single one is visible without a telescope. In fact, the smallest true star ever measured is only slightly larger than the planet Saturn. With just about 8% of the Sun's mass, it barely manages to sustain fusion. Were it any smaller, it would fail to ignite and become a failed star, known as a brown dwarf. By contrast, most of the stars we see sparkling in the night sky are the larger,
more luminous types that, while much rarer, shine hundreds or thousands of times brighter than red dwarfs and can be seen across great distances. If you stood on a hypothetical planet orbiting a red dwarf, the star might hang in a dim red sky, casting an eerie dusk, like light even at noon. By contrast, a planet around a hot blue-white star would be flooded with a stark, bluish illumination and intense ultraviolet rays. Size and mass have a profound effect on a star's fate. In general, the more massive a star, the hotter and brighter it burns, and the shorter its life. A star 10 times more massive than the Sun might emit thousands of times more energy, blazing a brilliant blue-white, but it will use up its fuel at an unsustainable rate. It's the difference between a gas, guzzling sports car and an economy car. The massive star burns through its fuel quickly, while a small star is extremely fuel efficient. Massive stars live fast and die young in a cosmic sense. Such a star might last only a few million years before it exhausts its core fuel. In contrast, a tiny red dwarf sips its hydrogen fuel so slowly that it can continue burning for hundreds of billions or even trillions of years. To put it in perspective, the universe itself is about 13.8 billion years old, so no red dwarf has had time to even come close to dying yet. Our Sun lies somewhere in the middle of the mass range. It's a G-type yellow dwarf, not exceptionally massive or small. It will have a total lifetime of roughly 10 billion years, moderately long by stellar standards. So far, the Sun has been shining for about 4.6 billion years, and it has about 5 billion to go before it starts to run out of core hydrogen. Because of these lifespan differences, no red dwarf star has ever died in the history of the universe. The universe simply hasn't been around long enough for the smallest, slowest, burning stars to use up their fuel. Even the oldest red dwarfs, born shortly after the Big Bang, are still shining today and will keep on shining for trillions of years to come. By the far distant future, long after bigger stars like the Sun have died, red dwarfs will be the last stars remaining, quietly glowing red in a fading universe. On the other end of the spectrum, many massive stars have lived and died in that same time, blazing through their fuel in a few million years and ending in catastrophic explosions. In a sense, the cosmos has a way of favoring the slow and steady when it comes to longevity. Eventually, even the most long-lived star will run low on fuel. When a star has fused most of the hydrogen in its core into helium, it starts to leave the stable phase of its life. The delicate balance that maintained the star for so long begins to falter. With less nuclear energy being produced in the core, the outward pressure that held the star up drops. The core, now largely helium, begins to contract under gravity since nothing is pushing back as strongly. And when the core of the star contracts, surprising things happen in the layers around it. The contracting core heats up a lot. This intense heat radiates into the surrounding shell of hydrogen that wasn't previously hot enough to fuse. Now that shell of hydrogen does begin fusion. So hydrogen fusion essentially migrates from the core to a shell around the core. Meanwhile, the helium core will eventually get hot enough to ignite a new kind of fusion. It will start fusing helium into carbon. The star's internal structure rearranges: a small, dense, very hot core fusing helium, and a shell around it fusing hydrogen. All this generates a tremendous amount of energy in the star's interior. The result is that the outer layers of the star are pushed outward, far outward. The star balloons in size. As the surface expands, it cools. The once yellow-white star becomes a cooler red star. It has now become a red giant. The term is literal. It is redder in color and gigantic in size compared to before. A star in this phase can swell to tens or even hundreds of times its original diameter. One day, about 5 or 6 billion years from now, our Sun will undergo this transformation into a red giant phase. As it approaches old age, it will exhaust the hydrogen in its core and begin fusing helium. The Sun's core will contract and heat up, and its outer layers will expand dramatically. In the process, the Sun's radius will likely grow so large that it engulfs Mercury and Venus, the two innermost planets, and comes perilously close to Earth's orbit. From Earth's perspective, the Sun would swell to an enormous red orb dominating the sky. The temperature on our planet would skyrocket. In fact, long before the Sun's surface actually reaches Earth, the intense heat will boil away Earth's oceans and atmosphere and render our planet uninhabitable. Essentially, a scorched, lifeless rock. There is a chance Earth might be swallowed up entirely by the Sun's expanded atmosphere, or it might just survive, parched and baked. Either way, the inner solar system will be unrecognizable. The Sun will not only grow in size, it will also lose a lot of its mass via a powerful stellar wind. With less mass, the Sun's gravitational pull on the remaining planets will weaken, causing those planets to drift outward to wider orbits. This red giant phase is a dramatic change, but fortunately for us, it's billions of years away in the future. For a star of the Sun's mass, this red giant stage is essentially the beginning of the end. After perhaps a billion years in the red giant phase, the Sun's core will have fused its helium into carbon and oxygen. It won't be hot enough to fuse those heavier elements, so the core will remain as a hot ball of carbon and oxygen. Without new fusion to support it, the core will contract further, and the outer layers of the Sun, which expanded so far out, will become increasingly unstable. In a series of pulses, those outer layers will be expelled into space, creating a brilliant cloud of gas around the dying star. This glowing shell of ejected gas is called a planetary nebula. The Sun, in its death throes, will thus cast off its atmosphere, which will drift away as an expanding bubble of gas. Planetary nebulae can be stunningly beautiful. Observed through telescopes, they appear as multicolored rings or shapes of glowing gas. In a few tens of thousands of years, the Sun's shed gases will mix into the interstellar medium, enriching it with elements the Sun made. All that remains of the Sun at this point will be its former core. This exposed core is a hot, extremely dense orb about the size of Earth. It's called a white dwarf, the final state of a low to mid-mass star like our Sun. A white dwarf no longer has fusion happening in its center. It is supported against further collapse by quantum pressure. It is, essentially, a stellar ember, an extremely hot cinder left over from the star's life. When it first forms, a white dwarf is incredibly hot and glowing white, blue, but it's also very small, so its total light is relatively faint. Over billions of years, it will cool and fade. To appreciate just how dense a white dwarf is, it packs roughly the mass of the Sun into a volume the size of Earth. Imagine compressing something as massive as a star into a ball only 8,000 miles across. The density of such an object is mind-boggling, on average about 1 million times denser than water, meaning a single cubic centimeter of white dwarf material would weigh on the order of 1 ton. In other words, a teaspoon of white dwarf matter would weigh several tons here on Earth. The gravity on its surface would be hundreds of thousands of times stronger than Earth's. If you somehow stood on a white dwarf, you would feel yourself weighing so much that you'd be crushed instantly. Over a very, very long time, a white dwarf will radiate away its heat and cool down. Eventually, after many tens or hundreds of billions of years, it would become a black dwarf, essentially a cold, dark, stellar remnant. In the case of our Sun, this is its ultimate fate, to spend eternity as a faint white, hot star gradually cooling into darkness. Indeed, most stars end their lives quietly as white dwarfs, simply cooling and fading away. Only the most massive stars end in the spectacular supernova route. Now consider a star much more massive than the Sun, say a star born with 10 or 20 times the Sun's mass, or even more. These stars go through their lives much more quickly and violently. They too will leave the main sequence once their core hydrogen is exhausted, but the sequence of events is even more extreme. Such a star becomes a red supergiant instead of a mere giant. One of the best known examples of a red supergiant is Betelgeuse, the bright reddish star in Orion's shoulder. Betelgeuse is about 15,020 times as massive as the Sun and has expanded to a tremendous size. Observations estimate it is on the order of 700–800 times the Sun's radius. If Betelgeuse were placed at the center of our solar system, it would extend well past the orbit of Mars and possibly even approach Jupiter's orbit. It's so large that its volume would encompass tens of millions of suns. And Betelgeuse isn't even the largest star known. A few rare hypergiant stars, such as UY Scuti or Stephenson 218, are believed to have radii around 1,500 × 2,000 times that of the Sun. Truly monstrous stars. These colossal stars are extremely luminous and short-lived. Betelgeuse, for instance, is only on the order of 10 million years old, yet it is already in its dying phase. In fact, Betelgeuse is expected to explode as a supernova in the relatively near future. It could happen anytime in the next 100,000 years, which is a blink of an eye for a star. It might be tomorrow, or it might be far beyond our lifetimes. We can't pinpoint exactly when, but we know the star is nearing the end of its life. When Betelgeuse does explode, it will likely shine as bright as the full moon in our sky for a few weeks and be easily visible even in daytime. What leads a star like Betelgeuse, or any other massive star, to such a violent end? The difference lies in what happens in the star's core after the hydrogen is used up. A high-mass star has the gravity and pressure to push the boundaries of fusion much further than a star like the Sun can. When hydrogen in the core runs out and the core contracts, the temperature soars high enough to ignite the fusion of helium into carbon and oxygen. Once helium in the core is exhausted, the core contracts and heats again, and the star's envelope expands into a red supergiant. But in these behemoths, the core gets hot enough to start fusing carbon into heavier elements. The pattern continues in a kind of fusion cascade. Carbon fuses into neon, magnesium, and sodium. When carbon is depleted, the core contracts and heats, and then neon fuses into oxygen and magnesium. Then oxygen fuses into silicon and sulfur. And finally, silicon fuses into iron and nickel. The star builds up onion like layers of fusion shells. Hydrogen burning in an outer shell, helium burning in a shell beneath that, carbon burning in a shell closer in, and so forth, all the way to a growing iron core in the center. The iron core is the final product of fusion, because fusion of iron doesn't release energy, it consumes energy. That's a crucial point. Up until iron, fusion can power the star, but once the core accumulates iron, further fusion would not yield net energy. So, as iron builds up in the core of a massive star, the star is living on borrowed time. The star continues burning elements in shells around the core, piling more and more iron into the center. Meanwhile, the time spent on each successive fuel is shorter and shorter. A massive star might spend millions of years fusing hydrogen, maybe 1 million years fusing helium, but perhaps only a few years fusing carbon, a few months fusing oxygen, and mere days fusing silicon into iron. Eventually, the iron core reaches a critical mass. At that moment, the star can no longer support its own weight. For a massive star, this is the final act, and it's dramatic. When the iron core can no longer hold itself up, it collapses catastrophically under gravity. This collapse happens incredibly fast. In under a second, the core implodes. The temperatures in the core skyrocket, and atomic nuclei get crushed together. Protons and electrons merge into neutrons, so the core essentially becomes one giant atomic nucleus, a ball of neutrons. The collapse is suddenly halted by the degeneracy pressure of neutrons. In that instant, the infalling material rebounds off the stiff neutron core. a powerful shockwave is sent roaring outward through the star's interior. The core collapse and rebound is so intense that it unleashes an enormous burst of neutrinos and a tsunami of energy. The star's outer layers are blown off in one of the most violent events in the universe, a supernova explosion. If the core of the star at the time of collapse is below about 2003 solar masses, it will become a neutron star, the ultra-dense, city-sized stellar remnant composed almost entirely of neutrons. If the core is above that mass threshold, even the neutrons cannot halt the collapse, and the core will continue collapsing into a black hole, a point of practically infinite density. Either way, the core's collapse triggers the supernova blast. In a supernova, the star's entire outer structure is ripped apart. The star's brightness increases tremendously for a short time. A supernova can briefly outshine an entire galaxy of normal stars. Imagine a single star suddenly shining brighter than 100 billion stars combined. That is what a supernova can do. It will radiate as much energy in a few weeks as the sun will in its entire 10 billion year lifetime. If such an event happens relatively nearby, it can be visible from Earth, even in the daytime. Human astronomers have indeed witnessed supernovas in the past. Historical records from East Asia and the Middle East describe guest stars appearing in the sky. For example, in 1054 AD, Chinese astronomers noted a new star that was visible in daylight for weeks. This was a supernova. Another supernova was observed in 1604. More recently, in 1987, a star exploded in the Large Magellanic Cloud and could be seen by the naked eye. In our own Milky Way, no supernova has been observed in the past 4 centuries, but statistically, we expect a few per century meaning we could be due for another any time in the future. In the chaotic violence of a supernova, there is a remarkable silver lining. This is the event that forges many of the heavy elements that enrich the universe. During the star's normal life, it created elements like carbon, oxygen, and silicon in its core. But elements heavier than iron, such as gold, platinum, and uranium, require the extreme conditions of a supernova to form. In the supernova blast, atomic nuclei slam together in rapid fire reactions, building up many of the heaviest elements on the periodic table. The explosion then scatters these newly forged elements out into space. The stellar ashes, carbon, oxygen, calcium, iron, gold, and so on, are flung far and wide, mixing into the gas between stars. Supernovae are therefore cosmic gardeners, seeding the interstellar medium with the ingredients for future generations of stars and planets. The very material that makes up our Earth and our bodies has gone through this cycle. The iron in your blood, the calcium in your bones, the oxygen that you breathe, those atoms were once created in the interior of a star or in a supernova explosion. As a NASA astrophysics team put it, we truly are made of stardust. The calcium in your teeth, the iron in your hemoglobin, the carbon in your DNA, all were forged in stellar furnaces. Indeed, without the carbon, oxygen, nitrogen, and other elements spread by stars, Earth could not have solid ground, air, or water, and life as we know it would be impossible. We owe our existence to stars that died long before the Earth formed. Indeed, without the heavy elements from stars, there would be no rocky planets, no air or oceans, and no living beings. Meanwhile, what's left of the star's core becomes either a neutron star or a black hole, as mentioned. Neutron stars are fantastical objects. Imagine something more massive than our sun crushed into a sphere only about 20 kilometers across. They are so dense that a single teaspoon of neutron star material would weigh around 1 billion tons on Earth. The gravity on its surface is so strong that if you dropped an object from 1 meter above, it would hit the surface in a microsecond, accelerating to millions of kilometers per hour. Neutron stars often spin rapidly, Some rotate multiple times per second and emit beams of electromagnetic radiation from their magnetic poles. As they spin, these beams sweep around like lighthouse beams. If such a beam points toward Earth periodically, we see pulses of radiation. These are observed as pulsars. The first pulsar was discovered in 1967 as a mysterious radio pulse every 1.3 seconds, so regular that the discoverers jokingly nicknamed it LGM-1, half, seriously wondering if it was a signal from an alien civilization. We now know it was a rapidly spinning neutron star. Pulsars can spin unbelievably fast. The fastest known pulsar rotates more than 700 times per second. Imagine an object more massive than the Sun, spinning hundreds of times a second. It defies the imagination. Some neutron stars, called magnetars, have magnetic fields even more extreme, up to 1,000 times stronger than a typical pulsar. A magnetar's field is so extraordinarily powerful that, at a few thousand kilometers away, it could disrupt electronics on Earth. Occasionally, magnetars undergo starquakes that release giant flares of X-rays and gamma rays. If the star's remnant core was too massive to form a stable neutron star, it continues collapsing beyond even the neutron stage. In that case, the core becomes a black hole, an object with gravity so intense that nothing, not even light, can escape from its vicinity. A black hole formed from a single star might contain, say, 5 or 10 solar masses of material, but all of that mass is crushed down into an infinitesimally small volume at the center. The region around it from which not even light can escape is called the event horizon, effectively the point of no return. For a black hole with the mass of our Sun, the event horizon would be only about 3 kilometers in radius. If the Sun was somehow compressed into a sphere only 6 kilometers across, it would become a black hole. For something as massive as Earth, the event horizon would be barely a centimeter across, meaning Earth would have to be crushed to the size of a marble to turn into a black hole. These numbers illustrate how incredibly dense and compact black holes are, matter and gravity in their most extreme state. Because no light comes from a black hole itself, we cannot see a black hole directly as a glowing object. A lone black hole floating in space would appear truly black, a gravitational trapdoor in the cosmos. However, we can detect black holes by their effects on surrounding matter. Often, a black hole will have gas around it. That gas forms a swirling accretion disk as it spirals into the black hole, and it gets extremely hot, often emitting X-rays that telescopes can detect. We also observe stars orbiting an invisible mass. For example, the center of our Milky Way galaxy has stars whipping around an unseen object, which we know is a supermassive black hole. In recent years, astronomers have even managed to capture direct evidence of black holes by imaging their silhouettes. In 2019, the Event Horizon Telescope project released the first picture of a black hole, or rather, of the glowing gas around a black hole's event horizon. It showed a ring of light and a dark central shadow, exactly as predicted by physics. This was the supermassive black hole in a distant galaxy. And in 2022, we finally saw a similar image of the supermassive black hole at our own galaxy's center. Black holes, once purely theoretical, are now actively studied cosmic phenomena. Amazingly, even after a star has died, its story might not be completely over. Sometimes, the remnants left behind can have dramatic afterlives. For example, if two neutron stars eventually orbit each other, they will gradually spiral inward over time. After millions of years, they may collide in a spectacular event called a kilonova, a merger explosion even more energetic than a typical supernova. Such mergers produce strong bursts of gravitational waves that propagate outward. In 2017, scientists detected gravitational waves from a neutron star collision and also saw a flash of light from it. This was the first time we observed both gravitational waves and electromagnetic radiation from the same event. That neutron-star merger forged copious amounts of heavy elements and scattered them into space. Black holes can merge with each other too. When they do, they emit a flood of gravitational waves. We can't see the merger, but detectors on Earth can hear the fabric of space tremble. In 2015, LIGO observed such signals for the first time, confirming a major prediction of Einstein's theories. These phenomena show that even in death, stars can continue to influence their surroundings in extraordinary ways. After a supernova fades, all that remains of the star may be a dense remnant, plus an expanding cloud of gas and dust, the supernova remnant. The ejected material from the star, now racing outward, sweeps up the surrounding interstellar gas and dust, creating a shell or complex filamentary structure that can glow for tens of thousands of years. The Crab Nebula, for instance, is the beautiful filamented remnant of the supernova of 1054 AD, still expanding at thousands of kilometers per second. Over time, these remnants disperse and mix with the interstellar medium, and here the grand cycle turns anew. The scatterings of old stars eventually become part of new nebulae, providing the enriched raw material for future stars. The next generation of stars will form out of clouds, seeded with the heavy elements of previous generations. Our Sun is thought to be a late generation star, born roughly 4.6 billion years ago from a nebula already seeded with heavy elements by earlier supernovae. Those elements made it into our Earth and into us. We truly are, as the saying goes, children of the stars. Stars, then, are not only beacons of light, but cosmic alchemists and recyclers. Through their life cycles, they transform the primordial hydrogen and helium into a rich array of heavier elements. And through their deaths, they redistribute those elements across space to fertilize new star formation. Generations of stars have built up the carbon in our tissues, the oxygen in the air, the silicon in rocks, and every atom of every element heavier than helium. The universe began with mostly hydrogen and helium, and it is the stars that fashioned all the rest inside their hot cores. It's a magnificent ongoing circle of stellar evolution and renewal, star birth, star life, star death, and new stars born from the remnants. This cycle has been going on for billions of years and will continue for billions more. It is the engine that drives the chemical enrichment and dynamic evolution of galaxies. When we survey the night sky filled with stars, we are gazing at a vast cosmic ecosystem in action. Each pinpoint of light has its own history and future. Some of those stars may be like our Sun, gently burning for eons. Others might be giant stars soon to explode, or faint red dwarfs just chugging along. There are hundreds of billions of stars in the Milky Way galaxy alone, and beyond that, billions of other galaxies each with their own billions of stars. The total number of stars in the observable universe is estimated to be around 10 to the 22. That's a 1 with 22 zeros after it. This number is so huge that it defies true comprehension. One popular comparison is that there are more stars in the universe than grains of sand on all the beaches on Earth. In fact, astronomers estimate there are on the order of 10,000 stars for every grain of sand on Earth. It's an astonishing thought. Next time you're at the beach, pick up a handful of sand and consider that the stars outnumber those tiny grains. Every one of those stars is a sun, and many of those suns have their own families of planets. The universe is teeming with stars beyond counting. Understanding the life cycle of stars gives us a profoundly richer appreciation of the night sky. When you next gaze up at the stars, remember that those twinkling lights are not mere points. They are distant suns, each with a life story spanning eons. The star that looks like a pinprick could be a giant blazing at millions of degrees, or a diminutive red ember glowing softly. Some of the stars you see tonight might already have exploded in the far past, their light only now arriving at Earth after traveling for centuries through space. In a very literal sense, we are connected to these stars. Our planet and our bodies are composed of star-born atoms. Indeed, without the heavy elements forged in stars, Earth wouldn't exist as a rocky world, and human beings could not have come to be. As the late astronomer Carl Sagan famously said, "We are made of star stuff." We are the universe's way of knowing itself, formed from the ashes of long dead stars.
In the end, the saga of stars is the saga of the universe. It's a story of creation and transformation on an epic scale, of diffuse gas gathering to ignite nuclear fire, of shining stability and convulsive death, of elements forged in celestial furnaces and cast into the darkness to become the seeds of new worlds. Stars have illuminated the cosmos for over 13 billion years, and they will continue to do so long into the future. Every twinkling star in the sky is a testament to the ongoing cycle of cosmic birth and rebirth. So the next time you find yourself under a starry night, take a moment to ponder the incredible processes happening above you. Those stars are distant suns, forging the stuff of life, exploding and renewing the galaxy. They light up the darkness and spark our imaginations. Theirs is a never-ending story, one of fire and dust, life and death, and renewal. An endless cosmic dance that has shaped our universe and, ultimately, made our own existence possible. And as long as you can see the stars shining overhead, you are witnessing a part of that grand story unfolding, a story that connects us all to the cosmos and to the dazzling stars that fill the sky. The final glow of the previous story fades, but our journey among the stars is far from over. In fact, it's only just beginning. Out in the cosmic dark, countless stars still beckon with new mysteries and deeper roles to explore. We have gazed upon the life cycles of stars, their births in nebulous cradles and their deaths in explosive finales. Yet there is even more to the stellar saga. Now, let us venture further into the galactic tapestry to uncover how stars themselves shape the grand story of the universe. As we continue, imagine drifting back in time to an era before even the first star ignited. In that primordial darkness, over 13 billion years ago, the universe waited for its first light. When the first generation of stars were finally born, they were unlike any that exist today. These population 3 stars, as astronomers call them, were forged from only the simplest elements, the sole ingredients created by the Big Bang. Theory paints them as cosmic titans, perhaps 30 to 300 times the mass of our Sun, and millions of times brighter. Such massive stars would burn their fuel ferociously fast, blazing only a few million years before dying in titanic supernova explosions. Yet in their brief lives, they performed a vital service. Their searing ultraviolet light rayonized the universe's hydrogen, ending the cosmic dark ages nearly 1 billion years after the Big Bang. In those first brilliant sparks, the universe transitioned from dark and opaque to radiant and transparent, a fundamental turning point in cosmic history. When those primordial stars lived and died, they also created something entirely new: heavy elements. In their hot cores, nuclear fusion began forging elements heavier than helium, carbon, oxygen, silicon, and more. And when the first stars perished as supernovae, they seeded the cosmos with these heavier elements. Before stars, the universe lacked the ingredients for planets or life. After the first stars, space was enriched with the star stuff from which future generations could build. It's awe-inspiring to realize that nearly all the elements in our bodies, the calcium in our bones, the iron in our blood, the oxygen we breathe, were forged in the hearts of stars that lived long ago. Those early explosions scattered the raw materials for new stars, new planets, and eventually us. Little wonder that astronomer Carl Sagan's poetic truth resonates. We are made of star stuff. The universe had to go through the fires of stellar furnaces,
to fill the periodic table beyond hydrogen and helium. With each generation of stars enriching the cosmic brew, subsequent stars were born with higher metallicity. Thus began an ongoing chemical evolution, each stellar generation shaping the composition of the next, gradually building up the complexity needed for rocky worlds and living beings. In the wake of the first stars, new generations of stars began to form from the ashes. Astronomers classify these stellar populations by their metal content. The ancient stars that followed the primordial ones are dubbed Population 2. They contain only a small trace of heavy elements, just a smattering inherited from those first supernovae. Many Population 2 stars still shine today. They are the oldest stars in galaxies, often found in the halos of galaxies or in ancient globular clusters. In fact, some globular star clusters in our Milky Way are nearly 13 billion years old, almost as old as the universe itself, and their stars preserve a fossil record of the early cosmos. These venerable suns are cosmic time capsules, their faint metal content telling us they formed when the universe was still poor in heavy elements. By contrast, Population Y stars, like our own Sun, are rich in heavier elements. Population I stars are younger, born later in cosmic history, from gas already recycled and enriched by countless prior stellar lives. They reside mostly in galactic disks and include many bright, hot stars, as well as middle-aged stars like the Sun. The distinction between these populations isn't just academic. It's central to understanding how galaxies formed and evolved. In the Milky Way, for example, the spherical halo of old Population 2 stars may be remnants of the galaxy's original build and early mergers, whereas the disk's Population 1 stars reflect ongoing star formation fueled by interstellar gas. The very structure of our galaxy, a thin disk with spiral arms, a central bulge, and a diffuse halo, has been shaped by the continuous birth and death of stars over billions of years. Early in our galaxy's youth, it likely underwent titanic mergers with smaller protogalaxies. One dramatic merger, revealed by the European Gaia spacecraft's star mapping data, occurred around 10 billion years ago when the Milky Way swallowed a dwarf galaxy, now nicknamed Gaia Enceladus, or the Gaia sausage. This cosmic collision delivered a vast influx of stars into the Milky Way's halo. The evidence is written in the motions and chemical makeup of many halo stars, which are distinct from native Milky Way stars, a sign that they originated in another galaxy. During such mergers, bursts of star formation likely ignited as gas clouds were jolted and compressed. Thus, the Milky Way's early history, the thickening of its disk, the build up of its stellar halo, was driven in part by starbirth sparked in the chaos of mergers. Time and again, galaxies grew by merging and forming new stars, with each generation of stars influencing the galaxy's structure and dynamics. Star formation itself tends to be a self-limiting and self-propagating process. Massive young stars radiate intense light and spew stellar winds, which can carve cavities in the surrounding gas. When the most massive of these stars go supernova, they blast the gas with shockwaves. This feedback can either trigger new stars or quench star formation. In dwarf galaxies, a few vigorous supernovae can blow out much of the gas, stifling further starbirth. In larger galaxies, star formation and supernova feedback regulate each other in a complex dance, ensuring that galaxies don't convert all their gas into stars at once. Indeed, observations show that the universe's star formation rate peaked about 10 to 11 billion years ago and has been declining ever since. At its height, galaxies were forming stars at a frenetic pace, so much so that today's rate is only a few % of that peak. Over billions of years, much of the free gas in galaxies has been used up or locked into stars, and energetic feedback from stars has kept a lot of remaining gas too hot to collapse easily. Our cosmos is slowly simmering down. Still, new stars continue to be born even now, especially in the rich spiral arms of galaxies. In our Milky Way,
Stellar nurseries like the Orion Nebula are actively turning out fresh stars. But the overall trend is inexorable. The fuel for star formation is finite, and eventually it will run low. Gazing far into the future, astronomers estimate that in roughly 100 trillion years, all the usable star-forming gas will be exhausted or locked up. By that far epoch, the era of star formation will draw to a close. The universe will transition into a quieter stage, dominated by the embers of stellar evolution, myriad white dwarfs slowly cooling into black dwarfs, neutron stars and black holes lurking in the darkness, and only the occasional new star flickering to life from the rare merger of two old stellar remnants. But fear not. At present, the universe is still richly populated with shining stars, and we live in a cosmos that is very much alive with stellar light. Let's turn our attention to the stars as architects of their galaxies. Every galaxy's visible beauty, its shimmering starlight, its glowing nebulae, comes from stars. Stars delineate the spiral arms of disk galaxies, with luminous young star clusters tracing out spiral patterns like celestial fairground lights. In majestic barred spirals and elegant ellipticals alike, the collective light of billions of stars gives each galaxy its form and color. Hot, young stars glow blue, white, giving star-forming galaxies a bluish hue, while older, cooler populations lend a yellow-red warmth to galaxy bulges and ellipticals. Thus, the mix of stellar ages influences a galaxy's appearance. A young, actively star-forming galaxy looks very different from an old, evolved system, precisely because of its stars. Over cosmic time, galaxies can even change type as their star formation slows. A disk galaxy may fade and redden into something more akin to an elliptical if star birth ceases and its blue stars die out. The grand narrative of galaxy evolution is intimately tied to the cycles of star formation within. Now consider not just individual stars, but stars in pairs and groups. It may surprise you to learn that most stars in the sky are not solitary like our Sun, but part of binary or multiple star systems. Imagine two stars locked in a gravitational waltz, orbiting a common center of mass. Such binary star systems are incredibly common, by some estimates, more than half of all Sun-like stars have a stellar companion. In these systems, stars can profoundly affect each other's evolution. Sometimes one star will swell into a red giant and transfer mass to its companion, an event that can spark explosive outbursts or novae. In fact, one type of supernova occurs in an elderly binary. A dense white dwarf star siphons gas from a companion until a runaway explosion is triggered, obliterating the white dwarf. These Type Ia supernovae are immensely important standard candles that have helped astronomers measure cosmic distances and the expansion of the universe. The discovery of the accelerating expansion of the universe, and hence dark energy, hinged on observations of distant Type Ia supernovae. Thus, an intimately interacting binary pair on the stellar scale produces a beacon visible across billions of light years, allowing us to gauge the universe's fate. In other binaries, two massive stars might evolve in tandem and eventually merge or collide. In globular clusters, such stellar collisions can produce the enigmatic blue straggler stars, stars that appear unexpectedly young and blue in a cluster of otherwise old stars. Blue stragglers are thought to form when two stars coalesce into a single, more massive star, effectively rejuvenating it. The result is a star that stands out as bluer and more luminous than it should for the cluster's age, a literal stellar oddball that reveals the cluster's dynamic past. The overcrowded cores of globular clusters facilitate such collisions, offering yet another example of how stellar interactions can yield peculiar outcomes. Some binaries consist of extremely exotic partners, for example, a neutron star or black hole orbiting a normal star. These systems can produce astonishing phenomena,
like X-ray binaries and even the recently detected gravitational waves. Picture a dense neutron star, essentially a city-sized atomic nucleus with the mass of the Sun, pulling gas off a companion star. As the gas spirals in, it heats up and emits powerful X-rays, making the binary shine brightly in X-ray light. In 1967, astronomers discovered pulsars. The first was affectionately nicknamed LGM-1 for Little Green Men 1, because its precise radio pulses were so mysterious, they were jokingly suspected to be alien signals. Soon, pulsars were understood as rotating neutron stars, the collapsed remnants of supernova explosions. In some binaries, two neutron stars orbit each other, gradually enspiraling as they radiate gravitational waves. In 2017, humanity observed for the first time the space-time ripples from such a neutron star merger, along with a dazzling multi-wavelength light show called a kilonova. That single event confirmed that neutron star collisions forge many of the universe's heaviest elements and demonstrated how closely stellar death and cosmic alchemy are intertwined. Similarly, the first direct detection of gravitational waves in 2015 came from a merger of two stellar mass black holes, remnants of massive stars that had danced together until coalescing. These gravitational wave discoveries opened a whole new window on the universe, essentially hearing the sound of stars merging in the dark. Through binaries and their sometimes violent interactions, stars have enabled us to confirm Einstein's theories, understand extreme states of matter, and even create new fields of astronomy. While many stars live in pairs or clusters, our Sun stands alone. Yet the Sun is no less influential for its solitude. It anchors our solar system, and its steady light allowed life to flourish on at least one world. The Sun's story is still unfolding. About 5 billion years from now, it will swell into a red giant, becoming so large that it engulfs Mercury and Venus, and possibly Earth as well. By then, Earth will be a scorched cinder. As the Sun expands, it will also begin to blow off its outer layers. In its death throes, it may create a beautiful planetary nebula, a glowing shell of expelled gas, before finally settling down as a white dwarf. This stellar remnant, about the size of Earth but containing nearly half the Sun's mass, will slowly cool like a fading ember for trillions of years. That is the long-range fate of our Sun and stars like it, to quietly shed their outer envelopes and leave behind dense cores. The galaxy will become littered with these white dwarfs, cosmic embers that, though faint, carry the memory of their progenitor stars. Even in death, stars continue to shape their surroundings. When a massive star explodes as a supernova, it leaves behind either a neutron star or a black hole. The expanding supernova remnant, a glowing cloud of ejected material E, can crash into surrounding clouds and trigger new rounds of star formation. Think of the Crab Nebula, the remnant of a supernova observed in 1054 AD. At its center lies a whirling pulsar energizing the nebula, and around it, the expanding filaments are rich in elements like oxygen, nitrogen, and iron, synthesized in the star's final moments. Those elements will eventually mix into interstellar space, seeding future molecular clouds. In this way, each supernova is both an ending and a beginning. An ending for a massive star, but a beginning for new stars that will one day condense from the enriched debris. Meanwhile, the neutron star left behind pours out winds of high-energy particles, sculpting and illuminating the nebula. A stellar corpse can thus continue to inject energy into the galaxy's ecosystem long after the star's death. Black holes, too, play a role. If a stellar mass black hole devours gas or stars, it converts that mass to energy, impacting the ambient gas. And on a galactic scale, supermassive black holes lurking in galaxy centers, themselves the end, products of stellar processes and mergers, can profoundly influence star formation in their host galaxies by blasting out energy. But those supermassive black holes are a tale for another time. In our story, we focus on the stars themselves, the little black holes they leave behind, and how even those contribute to the cosmic tapestry. Consider for a moment the sheer number of stars out there. Our Milky Way alone holds on the order of 100 to 400 billion stars. It's a figure almost beyond comprehension, and yet the Milky Way is just one of perhaps hundreds of billions of galaxies in the observable universe. If each of those has 100 billion or so stars, you get numbers like 10 more 22 stars in the observable universe. That's a 1 with 22 zeros after it, a quantity of stars truly staggering to contemplate. Each of those stars is a potential sun, perhaps with its own family of planets. In recent decades, we've learned that planets abound around other stars. The once singular idea of another solar system has given way to the realization that planetary systems are commonplace. Using missions like Kepler and TESS, astronomers have detected over 5,000 confirmed exoplanets so far, and counting. Statistics indicate that perhaps 1 in every 5 sun-like stars harbors an Earth-sized planet in its habitable zone. This means when you gaze up at the night sky, statistically the nearest sun-like star with an Earth-ish planet might be only a dozen light years away, practically next door on the cosmic scale. Planetary systems come in a dizzying variety: hot Jupiters, skimming their stars' surfaces, multi-planet systems packed in tight orbits, planets around double stars, and even planets orbiting the crushed remnants of dead stars. There are even planets wandering alone in the dark of interstellar space. Stars and planets are inseparable companions in the cosmic story, and just as stars give birth to planets, planets can influence stars in subtle ways.
Take our solar system. The sun's activity and stability have been key to life's development on Earth. Our sun is a rather steady star, but not all stars are so calm. Many young stars and red dwarfs are highly variable and prone to flares. Variable stars in general constitute a broad category, including stars that intrinsically pulsate, erupt, or have eclipsing companions, causing dips in light. These variations have made certain stars vital tools for measuring cosmic distances. For instance, the Cepheid variables, luminous pulsating supergiants, have a well-defined relationship between their pulsation period and true brightness. Discovered by Henrietta Leavitt over a century ago, this relationship allows astronomers to determine a Cepheid's distance by comparing its known true brightness to its observed brightness. Using Cepheids as standard candles, Edwin Hubble measured the distance to the Andromeda galaxy in the 1920s, discovering that Andromeda lay far outside our Milky Way, thus proving that the universe is populated with myriad galaxies. Later, Cepheids and Type Ia supernovae would help establish that the universe is expanding and, in fact, accelerating in its expansion due to mysterious dark energy. It's poetic that the rhythmic beating of variable stars' light has served as a cosmic yardstick, allowing us to map the universe at large. A throbbing Cepheid in a distant galaxy becomes a beacon, indicating that galaxies' distance, and hence offering insight into the scale of the cosmos. Not all variable stars are so regular and helpful. Some are downright capricious. There are flare stars that can double in brightness in minutes, eruptive variables like young stellar objects that burp out bursts of light as they gulp down fresh gas from their surroundings, and giants like Mira, a star in Cetus that pulsates over many months, varying so much that it can nearly disappear from view and then return. And who could forget the recent drama of Betelgeuse, the red supergiant shoulder of Orion? In late 2019, Betelgeuse dimmed startlingly, losing 2/3 of its brightness, causing speculation that it might be about to explode as a supernova. Observations eventually indicated that Betelgeuse had likely ejected a cloud of dust that temporarily obscured its light from our vantage point.
By mid-2020, Betelgeuse returned to normal. This episode was a vivid reminder that stars are dynamic, evolving entities, not static points of light. Betelgeuse is expected to go supernova sometime in the next 100,000 years, a blink of an eye in cosmic terms, and when it does, it will light up our sky brilliantly for weeks, a spectacular final act for a star perhaps 15,020 times the Sun's mass. If we're lucky enough to witness it, that supernova will be a momentous event in human skywatching history. But even short of such cataclysms, the variability of stars teaches us about their inner workings. Through the field of astroseismology, astronomers study tiny pulsations in stars to infer their internal structures, analogous to how geologists use earthquakes to probe Earth's interior. Our Sun, too, has a mild 11th-year cycle of activity, modulating its sunspots and flares, which subtly affects solar output. Thankfully, the Sun's variability is slight. A more erratic star might have made Earth's climate far less stable for life. Stars, then, are creators, testers, and timekeepers of the universe. They create the elements that form planets and people. They test the laws of physics in extreme conditions, from nuclear fusion in cores to relativistic speeds in neutron stars. They serve as timekeepers by revealing cosmic distances and ages through their life stages and variable rhythms. And collectively, stars brighten the universe, turning the primordial darkness into a cosmos of light and color. It is sobering and fascinating to realize that the universe's era of starlight is, in a sense, a finite chapter. We live roughly in the middle of this chapter. For billions of years before stars, the universe was dark, and trillions upon trillions of years in the future, after the last stars have flickered out, the universe will go dark again. But right now, and for many eons to come, it is the age of stars. An age in which galaxies sparkle and life has the opportunity to arise on warm, sunlit worlds. The story of stars is also the story of continuity and renewal. Massive stars live fast and die young, but in doing so, they trigger new growth around them. We see this in regions like the Carina Nebula, where the death of one generation seeds nebulae that birth the next. In a spiral galaxy's life, waves of star formation move through the disk, often stimulated by spiral density waves or past encounters with other galaxies. Our own Sun likely formed in a cluster with dozens or hundreds of other stars about 4.6 billion years ago, possibly triggered by a nearby supernova explosion that compressed our natal cloud. Traces of that supernova may be preserved in certain isotopes found in meteorites from the early solar system. Thus, the Sun and planets might owe their existence to the death of a long-gone massive star. Indeed, each of us carries the ashes of ancient supernova inside our bodies. The iron in your blood was forged in a star that exploded billions of years before the Sun even existed. In a very literal sense, stars are our cosmic ancestors. As we look ahead, what new revelations about stars await us? We stand in an exciting era of astronomy. The James Webb Space Telescope is now peering into the deep cosmos, possibly capturing light from some of the first galaxies and stars that formed over 13 billion years ago. Already, Webb has identified candidate galaxies so far away that they challenge our understanding of how quickly stars and galaxies could have formed. In the coming years, Webb may indirectly detect evidence of population 3 stars, or at least constrain their properties by observing the distant galaxies they inhabit. On the other end of the spectrum, Webb and other observatories are turning their gaze to exoplanet atmospheres, reading the fingerprints of molecules like water vapor, carbon dioxide, and methane as starlight filters through alien skies. In 2022, JWST made the first clear detection of carbon dioxide in an exoplanet's atmosphere, a proof
of concept for the detailed atmospheric analysis of potentially habitable worlds in the future. We are learning to read the chemical weather reports on planets dozens of light years away, an astounding development. Future missions will go even further. The upcoming Nancy Grace Roman Space Telescope will conduct vast surveys of the Milky Way's center, potentially discovering thousands of new exoplanets through microlensing and mapping out the distribution of stars and dark matter with high precision. The European Extremely Large Telescope, a 39-meter behemoth currently under construction, will in the next decade directly image some exoplanets and dissect the light of stars in distant galaxies, perhaps even detecting biosignature gases on rocky planets around nearby stars. It is mind-boggling. We are on the cusp of potentially finding evidence of life beyond Earth by examining starlight passing through a distant planet's atmosphere. Should we succeed, it would be a profound confirmation that we are not alone, all made possible by the interplay of stars and their planets. Even without finding life, the future of stellar astronomy is bright. New observatories will allow us to watch stars in real time in unprecedented ways, catching the precise moment a star goes supernova in our galaxy, or detecting the subtle vibrations of stars across our galaxy to decode their ages and compositions. We might witness phenomena we've only theorized, perhaps the birth of a black hole accompanied by a flash of neutrinos and gravitational waves, or the mergence of two white dwarfs into a new star or a supernova. We may even discover new classes of stars. Who knows? Throughout history, whenever we have opened new eyes on the universe, we've stumbled upon surprises. There could be rare types of stellar objects out there awaiting discovery, stars powered by exotic physics, or stars caught in transitions never before seen. The universe tends to be creative with its use of the physical laws. From the first luminous beacons that banished the cosmic night, to the ordinary middle-aged sun that sustains life on a blue planet, to the spectacular supernovae and gravitational wave chirps that herald stellar deaths. Stars have been the main protagonists in the cosmic drama. They are the alchemists that forged the elements, the lighthouses that guide our explorations, and the engines driving the evolution of galaxies. As we float here on our tiny world, bathing in the gentle sunshine of our star, we remain intimately connected to the lives of stars across the universe. Every atom of calcium in your bones was fused in a star that lived long ago and far away. Every gentle sunset tinged with reds and oranges is a reminder that our sun, too, will one day swell and cast a red hue over the sky of whatever beings inhabit Earth in the distant future. Yet even as individual stars perish, the universe ensures the torch of light is passed on. New stars ignite from the ashes, continuing the cycle. And so, the cosmic roles of stars are as profound as they are varied. Stars are creators of light, of elements, of new beginnings. Stars are destroyers. In their violent ends, they can obliterate companions or outshine entire galaxies for a time. Stars are storytellers. Their compositions and motions recount the history of their galaxies. Stars are guideposts. Their steady pulsations and explosions have built our cosmic distance ladder and expanded our knowledge of the universe's expansion. Stars are nurturers, providing warmth and energy to any orbiting planets, and perhaps nurturing life. It is often said that without stars, the universe would have remained a dull, cold fog of hydrogen and helium. There would be no planets, no complex chemistry, and certainly no people to wonder at it all. Indeed, without the stars, the universe would lack its narrative spark. Our exploration of the stars deepens our connection to the cosmos. When we look up on a clear night and see the Milky Way's band of light, we are seeing the integrated glow of billions of distant suns, many of them older, many younger, each on its unique journey from birth to death. Among them are red giants, white dwarfs, neutron stars, perhaps even black holes quietly lurking.
All of them together create the shimmering tapestry of the night sky. As we conclude this chapter of the documentary, let's reflect on the awe that stars inspire. For thousands of years, humans have looked to the stars for constancy, for navigation, for myths and meaning. Only in the last century or so have we truly grasped what they are. Nuclear furnaces, balanced by gravity, simple in their basic principles, yet endlessly diverse in their outcomes. And only in the last few decades have we come to see the universe on the largest scales and realize the full extent of the stars' role in shaping everything. The saga of stars is ongoing. Even now, new stars are being born in dusty nebulae. Old stars are blowing themselves apart. Binary stars emerging. Planets are coalescing around nascent suns. Life might be evolving in some distant solar system under the light of an alien star. And photons that left stars billions of years ago are just now reaching Earth, bringing us news from across the universe. With each advance in technology, we become better listeners and observers of the stars' messages. In the near future, we might map the surfaces of stars' light, years away, or detect the faint whispers of stars collapsing into black holes across the universe. And someday, perhaps, we will travel to other stars, our descendants, voyaging across interstellar space to touch those points of light that have beckoned for ages. For now, we continue to study and marvel. The stars have been our beacons, our ancestors, our catalysts. They will continue to shine for billions of years, but not forever. So it is a privilege to exist in this epoch of glittering skies. As our story winds down, step outside on a dark night and look up. Each star you see is part of a grand cosmic ecosystem. Some of those stars are likely orbited by planets you cannot see, perhaps harboring beings who look back at our sun as just another point of light in their sky. In the end, stars connect us across the gulfs of space and time. They are the universals, appearing in the sky of any planet in any galaxy, adhering to the same physics, telling variations of the same tale. This is the cosmic role of the stars, to light up the universe, to forge atoms from the raw stuff of the Big Bang, to sculpt galaxies, to cradle planets, and to continuously renew the cosmos. They are the glittering thread woven through the fabric of space, time, binding the universe together in light. And as long as stars shine, the universe will not be a lonely, lifeless place, for their light creates the possibility for beauty, complexity, and life. The story of stars is the story of how the universe, once a primordial soup of particles, became self-aware through creatures like us. We are the children of the stars, and through us, the stars know themselves. In the ever-continuing cycle of cosmic evolution, the stars have truly shaped the evolution of the universe, and they will continue to do so far into the future. So, whenever you stargaze, remember, you are watching creation in action, witnessing the ongoing drama that made all of existence possible. The tale of the stars is the tale of us all, a story still unfolding, written across the sky in the light of a billion suns. We float in the darkness between stars, a small collective of minds gazing up in wonder. We stand under the night sky, awash in starlight that left its sources millions of years ago. Above us arcs the Milky Way, a pale river of stars flowing across the heavens. In its gentle glow, we feel both tiny and profoundly connected. We know that each pinpoint of light is a sun like our own, burning with the same kind of fire. The iron in our blood was forged in such stars long ago. The gentle silver glow of the galaxy reminds us we are made of this universe. We have always been children of the stars, built from their dust, shaped by the physical laws that govern everything we see. The cosmos is vast and old, yet it obeys the same simple truths everywhere. The same chemistry that lets us breathe traces across the spectrum of distant suns. The same gravity that pulls an apple to Earth binds the swirling arms of distant galaxies. There is an eerie harmony to it all, as if the universe knows how to stay consistent with itself. We share this cosmic stage with countless stars and at least as many questions. On a clear night, as we peer into the depths, we find order amid the chaos. Galaxies dance in clusters, bound by gravity's invisible web. Stars live and die, spreading heavy elements that will become new stars, planets, maybe life. There are fundamental numbers, the strengths of forces, the masses of particles, the speed of light, that seem precisely tuned to weave this cosmic tapestry. If the forces of nature were only slightly different, perhaps atoms could not hold together, or stars could not shine long enough for life to arise. But here we are, in a universe that lasts billions of years, with stars that furnace the elements of life, and a planet just temperate enough for us to ponder it all. It's a breathtaking balance. In the grand cosmic darkness, the laws of physics serve as a steady beacon, guiding the formation of everything from the smallest atom to the largest galaxy. Our universe appears to be a harmonious whole, governed by elegant rules that we have only begun to decipher. Under this starry dome, it's natural to feel that our universe is complete unto itself. For generations, we've used the word universe to mean all there is, the totality of existence, everything that ever was or will be. We have believed, as Carl Sagan once poetically intoned, that the cosmos is all that is, or ever was, or ever will be. Our ancestors saw the stars as eternal and unchanging lanterns in the firmament. Today we know those lights are distant suns, but we still assume the collection of them, the universe, is the ultimate container of reality. It contains us, our planet, our galaxy, and all the far-flung galaxies we observe. It's immense beyond our imagination. Hundreds of billions of galaxies, each with billions of stars, spread across space that has been expanding for nearly 14 billion years since the Big Bang. Standing in the hush of a midnight landscape, seeing the infinite stars overhead, we are tempted to think this is everything, that beyond the glittering boundary of what we can see, there is only endless darkness. And yet, a question quietly rises, like the soft glow of pre-dawn. What if this isn't all there is? What if the magnificent expanse we call our universe is only one drop in a much grander cosmic ocean? As we let our eyes drift across the sky, we cannot help but wonder. We humans have had to expand our perspective many times before. Once, we thought our Earth was the center of everything, until we learned it is one planet among many orbiting the Sun. Then we thought our Sun was unique, until we found it is one star among billions in the Milky Way. We believed our galaxy to be the entirety of creation, until other galaxies were discovered, filling the universe in every direction. Each time, we've had to surrender a bit of our cosmic self-importance and accept that the universe is bigger and more varied than we knew. Now, a new revolution in thinking may be upon us, the idea that our entire universe might not be the only universe. Perhaps it is we who are in a bubble, one realm among countless others. The word universe, meaning everything, might itself be too limited. What lies beyond everything we know? This is the startling possibility that scientists and philosophers are grappling with in the idea of the multiverse, a multitude of universes, perhaps infinitely many, existing in ways we are only beginning to theorize. It sounds like science fiction, other universes with other stars, maybe even other versions of ourselves. Yet this concept did not arise from idle daydreams. It emerged from deep puzzles in physics and cosmology. As we peer closer at the fundamentals of our universe, its origin, its laws, its quantum underpinnings, we find hints that our cosmos might be just one of a far larger collection. Why is our universe so hospitable to life? Why did it start with just the right conditions for galaxies to form? What happens at the edges of space and time, or inside a black hole? Modern science suggests answers that lead to a profound outlook. our universe may be one node in an endless cosmic web of universes. For a moment, let's linger on that thought. If true, it would mean when we look up at the night sky, we are not just seeing all that is, but merely our own local neighborhood within an unimaginably vast ensemble. It would mean that beyond the cosmic horizon of 46 billion light-years, beyond the furthest galaxies we can ever see, space might keep going and going, potentially forever. And if space goes on forever, then logically, somewhere far beyond any hope of observation, there could be other regions of the cosmos entirely disconnected from ours, perhaps even following different scripts of reality. Could it be that the starry sky we see is like one page in an infinite book, a book with every possible page? The notion is as exhilarating as it is disorienting. Our heartbeats quicken at the bravery of asking such a question. Is our universe just one of many? We take a deep breath, steady our thoughts, and step through the looking glass into this radical idea. To explore the multiverse, we must journey back to the very beginning of our universe, to the first fraction of a second after the Big Bang. In that embryonic moment, according to our best theories, an extraordinary thing happened. The universe expanded at a stupendous rate, far faster than the speed of light, ballooning from subatomic size to astronomical size in the blink of an eye. We call this event cosmic inflation. It's a powerful idea developed in the 1980s to solve several riddles about the early universe. Why is the cosmic microwave background, the afterglow of the Big Bang, almost the same temperature everywhere we look? Why is space so flat and smooth on large scales? Inflation provides answers. A burst of exponential expansion stretched the young universe, smoothing out irregularities and flattening space, much like inflating a crumpled balloon. When we look at the sky today, the uniformity we see in the afterglow is the fingerprint of that inflationary era. The evidence for inflation has grown persuasive. Subtle patterns in the microwave background radiation and the distribution of galaxies align with what inflation predicts. It's not proven beyond all doubt, but most cosmologists have embraced inflation as a key chapter in our cosmic history. Yet inflation, in solving old mysteries, opened a door to an even grander possibility. The very equations that describe inflation imply that it may not have been a one-time event that neatly began and ended everywhere. Instead, inflation could be an ongoing process, still happening in distant regions beyond our view. The idea is called eternal inflation, and it works like this. Quantum fluctuations in the infant universe meant that different parts of space ended inflation at different times. Our entire observable universe is thought to be one pocket, one bubble, where inflation stopped and normal expansion took over, allowing matter to coalesce into galaxies and stars. But elsewhere, beyond our bubble, other regions might still be inflating or have inflated at different rates, budding off their own bubbles of space-time. In this picture, the Big Bang isn't a unique event. It's happening over and over in a vast inflating background. New universes, bubble universes, are constantly being born like foam on the crest of an endless wave. Imagine the multiverse as a great cosmic foam, with bubble universes instead of soap bubbles. Each bubble is a self-contained universe, rushing outward, separated from its siblings by regions of still inflating space that stretch faster than light, preventing the bubbles from easily colliding or interacting, though perhaps occasionally they might, like bubbles bumping in a bath. Our universe would be just one bubble in this frothy sea. Inside our bubble, we see the aftermath of our own Big Bang. We see galaxies flying apart as space expands, but our bubble has an edge beyond which we cannot see or travel. And beyond that edge, more bubbles, more Big Bangs, more universes. Inflation never completely ends. It keeps spawning new universes indefinitely, some perhaps even infinitely far away. This concept transforms the Big Bang from the beginning of everything to the beginning of our local universe, one patch,
amid an eternally growing mosaic. We find ourselves no longer at the center of the stage, not even the only stage. We are on one island, in an infinite cosmic archipelago. In this scenario, space itself is unimaginably vast, possibly infinite, and carved into domains, bubbles, each a cosmos in its own right. What would those other universes be like? They might be broadly similar to ours or wildly different. Some could be almost empty, inflation ending in them in such a way that few particles condense, barren voids with no galaxies. Others might be dense and violent, collapsing in on themselves or never cooling enough for stars. Crucially, the laws of physics might be different in each bubble. This isn't just speculation. It arises naturally when we combine inflation with another leading theory in physics, string theory. String theory attempts to unify all forces of nature by positing extra dimensions of space and tiny vibrating strings as fundamental ingredients. It's a bold, mathematically rich framework. One striking feature of string theory is that it doesn't predict a single unique outcome for the properties of our universe. Instead, it seems to allow a vast number of possible worlds, each corresponding to a different way the extra dimensions can be curled up or the strings can vibrate. Physicists call this huge range of possibilities the string theory landscape. Estimates suggest there could be on the order of 10 to 500 different self-consistent universes in this landscape. A number so huge, it defies comprehension. That's a 1 followed by 500 zeros, an astronomically large number of possible universes. If string theory's landscape is real, our universe is like a tiny oasis in a desert of possibilities. Why did we get this particular set of physical constants and not another? For decades, scientists hope to find a principle that picks out exactly our universe from the myriad possibilities, some fundamental reason our cosmos had to be the way it is. But so far, no such principle has been found. Instead, an idea gained traction. Maybe all those possible universes exist somewhere in the multiverse, and we find ourselves in this one because, out of the spectrum of possibilities, this is one of the rare universes where conditions allow observers like us to arise. This line of thinking is known as the anthropic principle, specifically applied to the multiverse. It says, consider that we can observe this universe. That simple fact biases what kind of universe we should expect to observe. We couldn't exist in a universe where, say, gravity was so strong that the universe collapsed in a second, or so weak that no stars formed. We couldn't marvel at the stars in a universe with no stars. So perhaps there are countless universes with varied physical constants, and naturally, we find ourselves in one of the Goldilocks universes. Not too hostile, not too sterile, but just right for life. This isn't a teleological or mystical argument. It's a kind of cosmic selection effect. Out of a multiverse of all sorts of universes, we, the observers, will only be in those universes that can support observers. It's a profound and somewhat unsettling idea. It means that many of the miraculous coincidences that make our universe habitable, the precise strength of the strong nuclear force, for example, which if slightly different would prevent stars from synthesizing carbon, or the value of the cosmological constant, the energy of empty space, which is so small that galaxies had time to form, might not be miracles at all, but simply one lucky ticket in a giant cosmic lottery. Our universe won the lottery of existence, allowing complex structures and life, but there were many, many tickets, universes, that were drawn. We naturally wake up in a universe that's a winner, because only winners get to have someone wake up and ask the question. This anthropic reasoning is controversial. Some scientists find it unsatisfying, akin to saying, we're here because we're here. Others point out that it did make a successful prediction. Decades ago, physicist Steven Weinberg used anthropic arguments to estimate the cosmological constant's value, reasoning that if it were much larger, galaxies wouldn't form and we wouldn't be here. His estimate was on the right order of magnitude to what was later observed as dark energy. That gave some credence to the idea that perhaps our universe's properties are drawn from a random distribution of possibilities across a multiverse. So inflation gives us a picture of an ever-growing, bubble-populated multiverse, and string theory suggests each bubble could have different physics, forming a patchwork of realities. The multiverse as a cosmic quilt, each patch a universe with its own pattern. We might inhabit a patch where the forces and particles are tuned just so, while far off in another patch, the fundamentals might be shifted. Maybe that universe has heavier electrons, or a faster speed of light, or even different numbers of dimensions. It boggles the mind to consider the variety. Many of those universes would be dull or inhospitable. Just as most of space in our own universe is cold and empty, most universes might not host life. But in an infinite ensemble, even rare conditions, like the specific mix that allows life, will occur infinitely often. Infinity has a way of making even the rarest outcomes inevitable somewhere. If space is truly endless and inflation eternal, then somewhere, right now, there are fantastical worlds. A galaxy where every star is encircled by habitable planets, or a universe where purple clouds of cosmic dust think thoughts. And also, scattered in the multiverse, would be countless worlds nearly identical to ours. In an infinite expanse, eventually the patterns of particles that make up you and me will repeat by chance. It's been estimated, in a straightforward infinite space scenario, that the nearest exact duplicate of our observable universe could be incredibly far, 10,118 meters away, a number so huge we can barely fathom it. But if space truly goes on forever, somewhere out there, that duplicate exists. And not just one, infinitely many. This isn't even invoking exotic theory. This is a consequence of simple infinity plus the finite ways particles can arrange. It's a mind-bending implication. The multiverse could contain other people who are, to all intents and purposes, you, living out every alternative history that could have befallen you. Before that notion makes us lose our grip, let's step back and approach the multiverse idea from a different angle. One that doesn't even require distant, unreachable corners of space, but might be unfolding right here and now, in tandem with our own lives. This brings us to the quantum realm, and to the many worlds interpretation of quantum mechanics. At first glance, this has nothing to do with the bubble universes of inflation. It's a separate thread, born from the mysteries of the subatomic world. Quantum physics famously tells us that particles can exist in a superposition of states. They can literally be in two or more conditions at once, like a spinning coin that is both heads and tails until we catch it. Only when we observe or measure the system does it seem to choose an outcome. For example, a single electron can pass through two slits at the same time and interfere with itself, a behavior which defies classical logic. In the traditional view, the Copenhagen interpretation, the act of measurement causes the set of possibilities to collapse to one actuality. Why or how that collapse happens is still debated. It's as if nature randomly selects one path for reality to take, out of many potential ones, at the moment of observation. In 1957, a bold young physicist named Hugh Everett III proposed a different solution. What if the wave of possibilities never actually collapses? What if instead, at each quantum event, the universe splits into branches, each branch realizing one of the possible outcomes? In one branch, the electron went through the left slit. In another, it went through the right. When you measured it, you became split as well. One version of you seeing the electron here, another version seeing it there. Each version is real, but they exist in separate, non-communicating parallel worlds. At the moment of measurement, reality's timeline forked. According to Everett's Many Worlds Interpretation, MWI, this is happening constantly, all around us, at the microscopic level, and by extension, at the macroscopic level too, since every big thing is made of quantum particles. The entire universe is continually branching into countless parallel universes. It sounds like something out of a fantasy novel. Every decision, every chance event spawns a new world. But this idea is grounded in the same rigorous mathematics
that makes quantum mechanics the most successful physical theory we have. Everett argued that if the equations say a particle can be in multiple states, maybe it truly is. And the only reason we experience a single outcome is that our consciousness follows a particular branch. Other outcomes play out as well, but we, this particular copy of us, only witness one. Another copy, another we, witnesses the other outcome, and neither version can interact or even know about the other after the split, because the whole universe's state has separated into non-interfering branches. Let's make this more concrete with a whimsical example. Suppose we flip a quantum coin, perhaps by measuring the spin of an electron, which has a 50-50 chance to be spin up or spin down, analogous to heads or tails. According to many worlds, when we check the result, the universe bifurcates. In one universe, we see the coin come up heads. In another universe, we see it as tails. In that moment, two versions of us emerge, each unaware of the other, each continuing forward, believing that our coin toss gave a definitive result. It didn't feel like a split. Each of us experienced a perfectly ordinary coin toss with a single outcome. But collectively, the deeper reality now encompasses both outcomes. Extrapolate this to every quantum event everywhere. Atoms decaying, neurons firing, photons reflecting. The rate of branching is beyond colossal. Effectively, with each fraction of time, the number of parallel universes multiplies, containing every possible way events could have unfolded. By this view, the entirety of creation is a constantly splitting tree, with trillions upon trillions of twigs sprouting each instant, each twig a full universe with a distinct history. It's an almost overpowering picture. If it's true, then right now there are unimaginably many versions of you living out other lives. Most of those versions are nearly identical to you, differing maybe only in what you had for breakfast yesterday or whether you sneezed an hour ago. Some are more divergent, versions of you who pursue different careers, live in different cities, speak different languages. For every choice you've ever wondered about, what if I had taken that other job? What if I had said yes instead of no? There is, if many worlds is correct, a universe out there where you did exactly that. Even for outcomes beyond your control. What if the storm hadn't hit? What if my favorite team won the championship? The alternatives happened in other branches. It's a multiverse not separated by distance, but by decoherence in quantum phase space. A fancy way of saying, the worlds occupy the same space, but cannot interact after they split, like ghostly layers of reality that are intangible to one another. They're here, but out of reach, each as real as the one we know. The many worlds multiverse is different in character from the cosmic bubble multiverse, but they're not mutually exclusive. In fact, if both theories are true, every bubble universe born from inflation might in turn branch into quantum many worlds, creating a kind of nested multiverse, an ever-branching fern of universes sprouting off other universes. But even on its own, the quantum branching idea profoundly changes how we see our place in reality. We might say, in a way, that the universe is remembering every fleeting possibility by giving it its own world. Nothing is forgotten or discarded. No potential outcome is truly lost. If something could happen, it does, each in its own branch. This notion of parallel worlds has seeped into popular imagination through science fiction, but here we're discussing it as a serious interpretation of physics. Many worlds has gained more acceptance among physicists in recent decades, especially as it offers a straightforward, if extravagant way, to make sense of quantum puzzles without requiring a special, ad hoc rule for observers. In many worlds, there is no mysterious wave function collapse. The wave function, the mathematical description of a system's possibilities, just keeps evolving smoothly. The collapse we perceive is simply us finding ourselves on one branch. In the grand scheme, the wave function of the cosmos contains all branches at once. From a bird's eye view,
There is just one quantum universe, one multiverse, evolving deterministically, encompassing every possibility. From our limited frog's eye view inside one branch, we see randomness and choice, not realizing the other outcomes also came true, just not in our world. As mind-boggling as the multiverse of many worlds is, we must acknowledge it might be unprovable in the usual sense. The alternate branches cannot be contacted. They drift out of phase permanently. Similarly, the bubble universes from eternal inflation are separated by more space than light can ever traverse, so we cannot see or travel to them. Critics of multiverse ideas often point out that if these other universes are forever unobservable, can we truly call this science? It's a fair question. Proponents argue that if a theory that we can test, like inflation, predicts a multiverse as a natural consequence, we shouldn't ignore that prediction just because it is difficult to verify directly. We might find indirect evidence or at least consistency checks. For example, while we cannot see other bubble universes directly, they might have, in rare cases, collided with our bubble in the distant past. Such a collision could leave a subtle round pattern in the cosmic microwave background, a bruise on the sky. Physicists have actually searched our sky maps for hints of such bubble collisions. So far, none has been convincingly found. If one day a circular anomaly in the microwave background were detected, consistent with another universe grazing ours long ago, it would be a groundbreaking, if indirect, confirmation that we're part of a multiverse. Similarly, with many worlds, while we can't hop between branches, experiments in quantum physics, like interference experiments with ever larger objects, continue to validate that superpositions are real. Many worlds takes those results to their ultimate conclusion. As our theories develop, we might even find more than one reason to believe in a multiverse. It's intriguing that completely independent lines of inquiry, cosmology on the largest scales, and quantum physics on the smallest, both hint at universes beyond our universe. And string theory, operating at the nexus of quantum gravity, adds its own multiversal flavor with the landscape of possibilities. These ideas paint different portraits of the multiverse, but they could be facets of one grand truth. Perhaps our reality has layers, the vast physical multiverse of regions beyond our view, sometimes categorized by physicists as Level 1 and Level 2 multiverses, with Level 1 being just an extension of our space, and Level 2 being different bubbles with different constants. The quantum multiverse of branching outcomes, Level 3 in one classification scheme, and even the ultimate abstract multiverse of all possible mathematical structures, Level 4 in that scheme. That last one, the Level 4 multiverse, is a conjecture by cosmologist Max Tegmark that every self-consistent set of laws, every mathematical structure that could describe a universe, is realized as its own universe. In such an ultimate multiverse, not only are constants different, but the very laws and fundamentals could differ. Universes with different numbers of dimensions, or entirely different particles, or physics beyond our imagining. It's a speculative idea, bordering on philosophy. In the realm of all possibility, nothing is forbidden. If such a Level 4 multiverse exists, our bubble of a universe is just one equation in the library of all equations. We mention this cosmic vision to acknowledge how far the multiverse concept can go. It's the broadest possible extension. Everything that can exist does exist in some universe. In a sense, it would answer the question, why is there something rather than nothing, by suggesting that nothing is just one option, but in the grandest multiverse, every option is instantiated. Thus, there is something, and indeed, everything. But even leaving aside that extreme level, the more grounded multiverse ideas give us plenty to ponder. Let's now gently descend from these theoretical heights and consider what it means for us if we truly live in a multiverse. How do we find meaning and identity in an existence where there may be countless duplicates of ourselves and innumerable worlds, with perhaps no obvious connection to ours? It can feel overwhelming, even disorienting, to contemplate that in the cosmic grand scheme,
Our entire observable universe, everything we've ever seen, might be a speck, and a redundant speck at that, one of infinitely many similar specks. It raises profound questions about significance, purpose, and uniqueness. One immediate question is about identity. We normally think each of us is a singular individual with a singular history. If the multiverse is real, especially the quantum many-worlds multiverse or the infinite space multiverse, then there are other yous out there. Some are extremely close to you, differing perhaps only by a single thought or atom's position. Others diverged more significantly at some juncture. Are those people you in any meaningful sense? Or are they merely separate individuals who happen to share your name and genetic makeup and memories up to a point? This isn't entirely abstract. Consider an analogy. Identical twins share nearly the same DNA and often a similar upbringing, but we still regard them as two persons. Parallel selves in alternate universes might be thought of similarly. Each one is a unique person, even if at one time they were the same person. Before splitting or before diverging, conditions made them different. We might need to rethink what we mean by self. Perhaps we're not an indivisible essence, but rather a collection of potential selves, only one of which we experience directly. In one philosophical view, inspired by the multiverse, who you are could be seen as a story, a narrative thread through one sequence of events. Your other selves have different narratives. Each narrative is valid and complete in its own universe. We, in this universe, are following one particular storyline. Our other selves follow their storylines. We branch like the limbs of a tree, sharing roots and trunk, our past, then splitting into separate boughs. Is the tree as a whole us? Or is each branch a different us? It might be a matter of perspective. There's a poetic notion in the multiverse context. We are like a branching tree or a splitting amoeba, continually dividing. The I that exists after a branch may not be aware of the other branches, but collectively, they all originated from the single organism that was I before. This can trigger a mini-identity crisis if we take it seriously. Am I just one of many? And if so, does my life matter less or more? One could argue it becomes more precious. I am the only version of me that gets to experience this particular sequence of events. Yes, there are uncountable other versions, but their experiences are theirs, and mine are mine. I, this branch of me, will never get to see what happens in the other branches, so for all practical purposes, my reality is the one I have. In that sense, nothing changes. I still must make choices and find meaning here. Alternatively, one could derive a sense of comfort that somewhere another me makes choices I regret not making, or achieves goals I failed to achieve, or keeps alive those I lost. But equally, somewhere I may experience tragedies I've been fortunate to avoid. It's a double-edged sword. What about morality and responsibility in a multiverse? If every possible outcome happens, does that diminish our responsibility for our actions? One might think, in another universe, I did otherwise, so what does it matter what I do here? But from the standpoint of each universe, consequences are very real. If I choose to be kind in this world, someone in this world is helped. That doesn't get erased by the fact that in another world, I might have been unkind. Each branch is separate and actual. We can't excuse misdeeds by pointing to another branch where we did good. Our local moral reality is what counts for us and those around us here. However, the multiverse could make us more empathetic to the range of human or cosmic experience. For anything someone can go through, there is likely a universe in which it occurs. It's a strange kind of consolation and caution at the same time. It might also challenge religious or spiritual views. For instance, if one believes in a guiding plan or singular purpose, a multiverse complicates that. Is there a separate plan for each universe, or one plan that encompasses all? If a deity exists, perhaps the multiverse concept elevates that deity's creativity to infinite heights.
creating not just one universe but a boundless array. Or conversely, some might feel the multiverse removes the need for a creator entirely, as it could explain fine-tuning without invoking design. These are deep waters where science and philosophy meet, and each of us may come to different personal conclusions about them. Let's step away from the heavy epistemology and imagine in a more playful way what the multiverse implies. It means every dream is somewhere a reality. Perhaps not literally the kind of dream you have at night, but any coherent scenario you can think of likely exists in some universe. A world where dinosaurs never went extinct and evolved intelligence. Physics doesn't forbid it, so it's probably out there in an alternate history. A planet where the continents formed a different shape, where an empire that fell in our history prospered in another timeline. The multiverse can be seen as a grand cosmic library of all possible stories. We happen to be leafing through one particularly engaging book, our life, our universe. But around us, on shelves stretching to infinity, are all other books that ever could be written. Some nearly identical to ours, some radically different genres altogether. This literary metaphor might bring a certain comfort. Our joys and sorrows, unique as they are to us, are also part of a vast tapestry of all joys and all sorrows that can ever be. We are not alone in any absolute sense. Existence in its totality contains others who have felt what we feel, done what we do, in one universe or another. In one sense, the multiverse can make us feel extraordinarily small, one tiny being, in one tiny universe, among who knows how many. But in another sense, it can make us feel profoundly connected, part of a much larger existence, threads in a boundless cosmic cloth. There is also the perspective of humility and open-mindedness that the multiverse invites. If our universe, the grandest thing we know, is just a drop in a sea, then the lesson of Copernicus continues. We are not the center, and even the reality we take for granted is not the whole show. That doesn't diminish the beauty of our world. In fact, it may enhance it. How special that, in an infinite multiverse, we have this particular universe to call home. Out of a multitude of possibilities, we get to experience this one, with its specific sky, its particular laws, its unique living Earth. It's like being dealt a particular hand of cards from an infinitely large deck. The odds of getting exactly this hand were infinitesimal, yet here it is, and it's the only hand we'll play in this game. That realization can instill a renewed awe for the gift of existence. We look at the sun and think, in other universes there may be different suns or no sun at all, but here we have this golden star warming our days. How marvelous. We taste a peach or listen to a melody and realize this experience might be rare in the grand ensemble of universes. What a privilege to be among the beings who can taste and listen. As we near the end of our journey through the multiverse, we find ourselves returning to where we began, under the canopy of stars, but with our minds expanded and our hearts contemplative. What have we learned? We learned that current science, as far as it has pushed, allows reality to be far larger and more varied than what we directly see. We learned that our universe might be just one wave on an endless ocean, one bubble in a boiling cosmic pot, one branch on an ever-dividing tree of realities. We entertained the possibility that our dearest laws and constants might be parochial facts, different in another universe, that our life here is one of many lives we might be living across parallel worlds. We considered how that might reframe our sense of self and our search for meaning. Yet after all that, we have also learned that the here and now still matters, perhaps more than ever. The multiverse idea, rather than making everything meaningless, can make everything meaningful in its own local context. Each universe is like a poem, complete in itself. The existence of other poems doesn't reduce the beauty of this one. Our narrative, the story of us in our universe, is still unique to us. We remain the authors of our choices and the caretakers of our world. If indeed the cosmos is remembering every possibility through the multiverse,
then living our lives authentically is our way of contributing to that cosmic memory. We are the universe, or multiverse, experiencing itself in one of myriad forms. There's something profoundly poetic about that. It suggests a unity behind the diversity. Just as millions of cells make up one organism, perhaps countless universes all exist within one overarching reality. We might never observe those other universes, but through science and imagination, we can feel a sense of their presence. In a way, contemplating the multiverse brings us a sense of companionship in the cosmos. The vast loneliness one might feel, thinking of how empty most of space is, could be alleviated by imagining that beyond our horizon are other universes brimming with their own wonders. Some might harbor life, minds, civilizations, utterly alien or perhaps oddly familiar. We cannot know, but it's intriguing to think that creation did not stop with our world or our universe. Nature, it seems, never runs out of creativity. The multiverse would be the ultimate expression of fecundity, an infinite garden of worlds where all possibilities bloom. Now, as we let these ideas settle, we might worry. Will we ever be sure the multiverse is real, or will it remain forever a tantalizing hypothesis? It's possible we may find stronger evidence, a clear sign of a universe beyond ours imprinted in subtle data, or a theoretical breakthrough that virtually demands the existence of other universes. Or we may find that our theories were mistaken or incomplete, and the grand multiverse doesn't exist as we conceived. That is the nature of science. It evolves. But whether or not the multiverse is physically true, exploring it in our minds has value. It stretches our imagination and challenges our assumptions about reality. It teaches us not to take everything for granted as truly everything. There may always be more beyond, unknown domains to discover or conceive. In the end, thinking about the multiverse is a bit like standing at the shore of an endless sea at night. We see the dark waves and hear their roar, but we cannot see across to the other side. In fact, there may be no other side. We know not what lies over the horizon of water and darkness. It could be more ocean, stretching out without limit. We suspect it is. And perhaps, out there in the cosmic ocean, there are other explorers on other shores, under other skies, wondering if anyone else is out there. In our universe, on our small planet, we've long wondered if we are alone in the cosmos. The multiverse concept extends that wonder to our universe itself. Is our universe alone or one of many? It is a profound shift of perspective, yet somehow a natural continuation of the trajectory we've been on since Copernicus. Every time we thought we were singular, we found we were part of a multitude. Why should universes be any different? Nature has shown a love for prolific abundance, countless stars, countless galaxies. Perhaps it also made countless universes. As we conclude this exploration, let's allow ourselves a moment of quiet reflection and awe. Above us, the night is still and clear. The stars shine down indifferently, as they have long before we understood any of this. We realize that even if there are infinite universes, we still only see our sky, and it is beautiful. The multiverse, if it exists, doesn't make our universe any less wondrous. In fact, it makes every glint of starlight even more poignant, knowing that it might be one of uncountable stories. And yet it is our starry sky, our chapter of the cosmic tale. We feel a sense of gratitude for being alive in this vast, enigmatic reality, whatever its true extent may be. We turn our gaze from the heavens to each other. We, the collective voice in this narrative, represent all of us together, trying to understand existence. In confronting the idea of the multiverse, we have shared a journey of imagination grounded in science, and science elevated by imagination. It's a journey that has taken us to the borders of knowledge and beyond, into realms that test the limits of language and thought. Such a journey can be humbling. It reminds us that there is so much we don't know, but it can also be inspiring. It shows that we as humans
have the capacity to envision realities far beyond our mundane experience. Perhaps, someday in the distant future, our descendants will find ways to gather more evidence or even harness knowledge of the multiverse. Or maybe the multiverse will remain an eternally tantalizing concept, never fully confirmed. Either way, it changes us in the here and now. It expands our conception of what reality could be. It invites us to partake in a cosmic perspective that is at once deeply intellectual and deeply spiritual, acknowledging the possibility of infinity and the mystery that comes with it. So, what if this isn't all there is? Then our stars and galaxies are just one refrain in an endless cosmic song. Does that make them any less melodious? No. To us, they are everything, and they are precious. And if in addition, the choir of creation is larger and more complex than we knew, then there is even more reason to be filled with reverence and wonder. We close our eyes and imagine for a moment, countless universes shining like bubbles in a vast foam, or like an orchard of worlds stretching out beyond sight. We imagine each universe has its own sky, perhaps its own version of someone looking up and feeling small yet curious. In this grand symphony, we, in our universe, contribute our part. A small, clear voice in an unspeakably large choir. The song is one of existence, exploring all possibilities, and through science and storytelling, the cosmos, or multiverse, finds a way to know itself through our eyes and our understanding. Now we open our eyes again to the familiar stars above. They seem a little kinder now, as if winking at a secret we've shared. The night breeze is cool, carrying the earthy scent of our world, our dear world that nurtured us. For all this talk of other universes, it is here that we love and strive and wonder. Here is where we make our meaning. The multiverse has not answered the question of meaning for us. Instead, it has enriched the context in which we ask it. Meaning, it seems, is ours to create, in whatever corner of the multiverse we inhabit. We stand together under the cosmos, humbled by its vastness, yet uplifted by its possibilities. We feel small, but not insignificant, transient, but not pointless. We are part of something so much larger, and that realization does not diminish us. It ennobles us. It means the adventure of discovery will always continue. There will always be new horizons to explore, new questions to ask. Our universe was once unknown and mysterious, and we have made it familiar. If there are other universes, perhaps one day, in some form, they too will become part of the purview of understanding. Until then, we carry the torch of curiosity forward, illuminating what we can and respecting the darkness of what we cannot yet see. In the multiverse of ideas, we have voyaged through reflections and dreams, through mirrors and branching streams of time. It's time now to gently return to our own world. We take one last, long look at the stars. The night is deep and silent. In that silence, there is a whisper of infinity. We sense the multiverse not as an abstruse theory, but almost as a presence, a silent chorus behind the curtain of reality, singing possibilities. And we, tiny though we are, sing along by simply living our lives and seeking truth. When dawn comes and the stars fade, we will go about our day, but perhaps with a renewed sense of wonder. Maybe we'll pause and think, the light of this morning sun could be rare in the multiverse. Let me feel its warmth with gratitude. The loved ones I speak to, the act of kindness I can do. In this universe at least, these matter immensely. The multiverse, if it exists, is not an escape from our reality, but a profound backdrop that can make our reality even more meaningful. As the first hint of morning glows at the horizon, we conclude our journey. We went seeking the multiverse and found that, whether or not it's truly out there, it has already expanded our minds. We end not with an answer, but with a feeling, the feeling of awe. Awe at the richness of the cosmos, awe at human ingenuity to even conceive of the multiverse,
and awe at our own capacity to find meaning and connection in a possibly infinite expanse. Our story, the story of one universe awakening to the potential of many, becomes a kind of cosmic meditation. We step forward into the daylight, carrying this perspective with us quietly. The question, what if this isn't all there is, will continue to echo, inviting further exploration. And whenever we need to rekindle our sense of wonder, we know we can look up at the night sky, remember the grand vision of the multiverse, and feel that childlike spark again. In the face of eternity and infinity, we find not despair, but endless possibility. Our journey through the multiverse has been like traversing a hall of mirrors, each mirror reflecting a different face of reality. Now, back in our own mirror, our own universe, we smile, a small, knowing smile, because we glimpsed the hypothetical reflections and returned wiser. We carry within us the stories of myriad universes, and that makes the story of our universe all the more precious. In that spirit of appreciation and wonder, we conclude our exploration. The multiverse, real or not, has given us a gift, the gift of cosmic perspective. With it, we walk gently through our world, eyes open to the stars, hearts open to the unknown, and minds ready to embrace whatever truths the cosmos has yet to reveal. We are humbled, we are inspired, and above all, we are connected to each other, to our universe, and maybe, just maybe, to all universes. Before the beginning, there was nothing. Not the nothing we know. A quiet room, an empty sky, those are still somethings. This was a deeper void, a profound absence of anything at all. No space stretched black and empty, for space itself did not exist. No time flowed, for even time had not yet begun. There were no stars, no galaxies, no light, no darkness. There was not even the void, not even emptiness. For even a void is somewhere, and here, there was no where to speak of. It was nothing. And in this nothingness, in this silence before creation, lay a mystery, an infinite stillness pregnant with potential, poised on the cusp of existence. Yet even in this absolute nothingness, one might imagine a quiet anticipation. If silence could dream, perhaps it would dream of sound. If emptiness could yearn, perhaps it would yearn to be filled. In that abyss before time, there was no watcher to perceive it, no mind to ask questions, only a possibility, waiting, without knowing that it waited. And then, in a moment, beyond moments, it happened. From the void, a spark of unimaginable brilliance and energy burst into being. In an instant, outside the realm of time, the universe was born. One moment, there was nothing. The next, there was everything, unfolding from a single, infinitesimal point. It was not an explosion in the way you might think, for there was no pre-existing space for it to explode into. It was an unfolding, an unfurling of space and time from within, like a flower blooming in absolute darkness, a tiny point containing all that would ever be suddenly blossomed, and space-time itself began to stretch and grow. I was born. I, the universe, came into existence, carrying everything, all things, all energy, all matter, all the dimensions of space and time within me. In that first indescribable fraction of a second, I was incredibly hot, incredibly dense, and oh, so small, smaller than a proton, smaller than a grain of sand, yet containing the entirety of what would become the cosmos. All that I am now, trillions of galaxies, endless space, energy beyond measure, was crammed into a point of infinite potential. My birth was not a gentle unfolding, it was a torrent of creation. Space itself raced outward, expanding at a mind-boggling rate. In truth, even words like outward fail, for there was no pre-existing space outside of that tiny primordial speck. Space was creating itself as it expanded. In the barest instant after the beginning, I underwent a sudden, explosive growth spurt. Your scientists call it inflation, a moment when I swelled at a rate beyond comprehension. Imagine something smaller than an atom blossoming to the size of a galaxy in a sliver of a second. Faster than any speed you can fathom, faster than light itself, space unfurled, carrying energy with it. Distances between points grew so rapidly that what was once near became unimaginably far in the blink of an eye. It was as though I drew a sudden deep breath. One moment I was microscopic, the next I was astronomically vast. Every part of me rushed away from every other part. This was no ordinary expansion. It was space itself stretching, like an elastic fabric pulled taut. Had there been an observer, and there was none, they wouldn't have seen an explosion from a point outward. They would have found themselves in that point as it expanded, with every distant region racing away. Think of a balloon being blown up. Every point on its surface moves apart as the balloon grows. So it was with space during inflation, every region speeding away from every other, no center, no edge, just an ever larger space for reality to inhabit. During this wild inflationary epoch, I was almost perfectly smooth and featureless. Almost, but not entirely. Even in that near uniformity, tiny imperfections existed, like the faintest of ripples on a glassy sea. These were quantum fluctuations, minuscule, random variations, little densifications and rare factions of energy, born from the jittery uncertainty ingrained in the fabric of reality. If the early universe were a calm, glowing ball, these fluctuations were slight dimples and pimples upon its surface. Inflation took these microscopic irregularities and blew them up in size. What had been subatomic wrinkles were stretched to astronomical scales. They were unimaginably small in origin, but they would become immeasurably important. For in these seed imperfection, these whisper-light variations, lay the blueprint for everything to come. The clustering of matter into galaxies, the gathering of gas into stars. In an almost perfectly smooth newborn cosmos, these tiny fluctuations were destiny in embryo. All the while, in that first second of existence, the fundamental forces of nature were taking shape. Initially, all forces were one, merged in a high-energy unity. There was no separate gravity or electromagnetism or nuclear forces, just a single, unified force, elegant in its symmetry. But as I expanded and cooled just a little, this symmetry began to break. It was akin to a white light separating through a prism into a spectrum of colors. Where once there was a single radiance, now there were many hues. Gravity was the first to separate from the unity, tugging at the expanding fabric of space, announcing itself as the force that shapes the macrocosm. Next, the strong nuclear force crystallized out, destined to bind atomic nuclei together. Then the electroweak force split in two, the electromagnetic force, which would govern light, electricity, and magnetism, and the weak nuclear force, responsible for certain subtle particle transformations. What was one became many, like a single note breaking into a chord. The laws of physics as we know them were being written in those moments, set into the fabric of the young universe. The great cosmic symphony was tuning its instruments. Inflation lasted only an eye blink of time, and then it subsided as abruptly as it began. The expansion didn't stop, but it slowed to a more gentle rate. In the wake of that sudden growth, my contents, space, time, energy, were spread out and cooling. Still hot beyond imagination, but cooler than that first instant of fury. With that cooling, something profound happened. Energy began converting into matter. In that early fireball, energy and matter were two forms of the same coin, constantly changing one into the other. From the blazing energy of creation, the first particles condensed, like drops of rain precipitating from a humid air. Tiny fundamental particles, quarks, electrons, and others, popped into existence. They did not appear alone. Each particle had its mirror twin, an antiparticle. For every quark, an antiquark. For every electron, a positron. Matter and antimatter, twin sides of a coin. And when these twins met, they did what twins often do in such close quarters. They annihilated one another in a burst of light. It was a fierce and frenzied dance, particles blossoming out of energy, then colliding with their antiparticles and converting back to energy. Creation and destruction intertwined, happening everywhere, all at once. It was as if each particle had a mirror image, and when the two touched, they cancelled each other out in a flash, like a perfect reflection, disappearing when the mirror is removed. The universe was a cauldron of radiant energy, partnerships in a primal dance, annihilating each other in brilliant flashes. For a time, it seemed a stalemate, matter and antimatter created in almost equal amounts, erasing each other as fast as they appeared. But there was a tiny bias in the gears of reality, a slight preference for matter. For reasons still mysterious, for every billion matter-antimatter pairs that annihilated, one extra particle of matter survived without a partner. It was a small imbalance, 1 part in a billion, but that was enough. As the fire of those early moments raged and then began to subside, these lonely survivors became the seeds of a material universe. A nearly imperceptible excess of matter over antimatter, just a few grains of sand left on a vast beach after the tide recedes, would become everything, every star, every planet, every living being. What a fragile beginning for all the substance we find around us. But it was enough. When the fury of mutual annihilation finally settled, a soup of particles remained, mostly photons, particles of light, along with neutrinos, ghostly particles that rarely interact, and those leftover protons, neutrons, electrons, matter unpaired with antimatter, ready to form the building blocks of atoms. Time was still less than a second old, but so much had already transpired. As I continued to expand and cool, the nature of the cosmos changed. Quarks, which had been bounded only by energy, now joined together in triplets, forming the first protons and neutrons. By the time I was a mere millionth of a second old, I was a swarm of particles, quarks bound into protons and neutrons, electrons zipping through a dense plasma, neutrinos flying free, and an ocean of photons bathing everything in a blinding glow. My temperature was staggeringly high, billions upon billions of degrees. In such heat, protons and neutrons moved at fantastic speeds, colliding frequently, and in those collisions, some stuck together. A proton and neutron fused to form deuterium, a heavy form of hydrogen. Deuterium nuclei combined to form helium. In those first minutes, about 3 minutes after it all began, I became a cosmic nuclear reactor. The entire universe was like the core of a star, forging light elements in a rush. By the time I was about 5 minutes old, this flurry of nucleosynthesis had created a primordial mix of matter, about 3/4 hydrogen nuclei and 1/4 helium nuclei, with a trace of lithium and other very light elements. The basic chemistry of the cosmos was established in those first few moments. The first fusion had happened on a universal scale, hydrogen fusing into helium, releasing energy, shaping the elemental content that would later feed the first stars. After those furious first minutes, I continued to expand and cool. The temperature, while still incredibly high, fell below the threshold needed for fusion. The nuclear reactions ceased, leaving the abundance of hydrogen and helium fixed. What remained was a hot, dense plasma, an opaque fireball of electrons, protons, helium nuclei, and photons, all intertwined in a seething dance. For thousands of years, I was just such a blazing, blinding cloud, brilliant but hidden behind its own light. Photons, particles of light, couldn't travel freely. They ricocheted off electrons and protons like a frantic crowd, shoving and jostling, never getting far before bumping into someone else. The universe was brilliant, but that brilliance was trapped, scattered endlessly within. As I expanded further, the energy density of radiation, light, dropped faster than that of matter. After about 47,000 years, matter began to dominate radiation in driving my evolution. Gravity had more say than radiation pressure. Space kept stretching, and with it, the wavelengths of the photons lengthened, cooling the radiation. What was once an intense, short wavelength glare stretched into a softer glow. Millions of years passed. By the time I was a few 100,000 years old, the temperature had dropped to a few thousand degrees, cool enough for a subtle but vital change. The free electrons, which had been careening wildly, combined with protons and helium nuclei to form neutral atoms. Electrons settled into orbits around nuclei, the plasma became a gas, and suddenly, the universe underwent a transparency revolution. Before, any photon would immediately hit a charged particle and bounce off. But now, with most electrons bound into atoms, light could at last travel freely. It was as if a dense fog had lifted, or a veil had been drawn away from the face of the cosmos. In that moment, the first light that had been trapped since the dawn of time burst forth and streamed across space. The universe, which had been opaque, became clear. A great glow permeated everything, a warm, diffuse radiance shining everywhere at once. To any hypothetical observer then, though none yet existed, the sky would no longer be an intense white furnace. It would have cooled to a brilliant orange hue, like the embers of a cosmic fire spread across the heavens. And as time went on and expansion continued, that orange glow faded to red, and then, beyond red, into invisible warmth. What was left of that light after billions of years would be a faint, cold whisper of its former self. In fact, that ancient light is still around even today, stretched into microwaves, the cosmic microwave background, a soft afterglow of creation that fills the sky in every direction, testimony to those early times. So, about 380,000 years after my birth, I was a very different cosmos than at the first instant. I was vast and growing, filled with a cooling gas of hydrogen and helium, and bathed in a gentle afterglow. That afterglow light, having been released, simply traveled onward, diluting and weakening as space expanded. The once blinding brilliance had become a faint luminescence. As it stretched to longer wavelengths, visible light gave way to infrared, then to microwave. Darkness, at least to human eyes, descended for a time, the first cosmic darkness since the moment of creation. Now the stage was set for a new chapter. Gravity, which had patiently been pulling at every density fluctuation since the beginning, began to work its magic more noticeably. Remember those tiny ripples, those minuscule fluctuations in density from the era of inflation. In this new, matter-dominated era, their effects began to grow. Wherever matter was even slightly denser than average, gravity exerted a slightly stronger pull, drawing in nearby gas ever so gently. Regions that had a bit more matter attracted more matter, and thus grew even denser, while emptier regions gave up matter to their neighbors and became emptier still. Over millions of years, the once nearly uniform gas developed a texture. A cosmic web of structure started to emerge. Unseen particles of mysterious dark matter, matter that neither emits nor absorbs light, had already begun to clump as well, their gravity forming scaffolds that helped ordinary gas fall into patterns of filaments and clusters. What began as tiny density differences in the primordial fireball now manifested as great clouds and strands of gas stretching across newly forming space. It happened slowly, imperceptibly at first. For a long time, to any observer, it would have seemed that nothing was changing. The universe was just a dark expanse of cooling gas. But gravity was relentlessly pulling, gathering, sculpting. Over tens of millions of years, gas drew into titanic filaments hundreds of millions of light years long and concentrated into nodes at the intersections of those filaments. It was as if an invisible hand were sketching patterns on the blank canvas of darkness, tracing the faint blueprint left by those primordial whispers. In 3 dimensions, these filaments and nodes formed a structure akin to foam, like a sponge or a vast spiderweb, with matter lining the threads and enormous voids between. The smoothness of the young universe gave way to a delicate, lace-like structure, a cosmic web of matter. Within the densest knots of that web, proto-galaxies were forming. These were the seeds of galaxies, vast clumps of gas, mostly hydrogen, some helium, gathering under their own gravity. They were not yet the glittering star cities we know as galaxies today, for they had no stars, not yet. They were like dark, nebulous clouds, quietly accumulating mass in the cosmic night. You could have traveled for tens of thousands of light years across one and not seen a single star, only the faint glow of the residual heat and perhaps the very, very dim molecular emission of cooling gas. These proto-galactic clouds grew in mass and began to fragment into smaller, denser pockets within. Think of a giant cloud many light years across, breaking into clumps, each clump destined to become a star cluster. Inside those clumps, the first stars were about to ignite. Gravity drew gas inward, tighter and tighter. As a clump contracted, it spun faster, like a twirling skater pulling in their arms, and flattened into a disk. At the center of this disk, gas piled up, growing ever hotter and denser. Imagine an enormous cloud core, 100 times the mass of our sun, collapsing under its own weight. The temperature in the core climbed to millions of degrees. All the while, the gas was being squeezed, compressed by its own gravity, the atoms crowding closer and moving faster. There comes a moment when the pressure and temperature at the core of a collapsing cloud become so high that hydrogen nuclei begin to fuse together to form helium. And with that fusion, a vast amount of energy is released. For the first time in cosmic history, a star blazed forth. It happened in many places around roughly the same era, over a span of a few 100 million years. But we often speak of the first star as a symbol of them all. In one of those dark proto-galaxies, in a dense pocket at the center of a collapsing gas cloud, there was a sudden outpouring of light. A brilliant, blue-white radiance flooded out from that point, the dawn of starlight. The cosmos that had known only diffuse, background glow now had point sources of light, shining fiercely like new candles lit in a dark room. The cosmic dark age was ending. The cosmic dawn had arrived. The first stars were not like the stars that twinkle in our familiar night sky. These were giants, monsters of brilliant light and short life. They were made almost entirely of hydrogen and helium, for those were the only elements the universe had at that time. Lacking heavier elements, the gas cooled less efficiently, which meant the stars that formed tended to be very massive, tens or even hundreds of times the mass of our sun. They burned hot and blue, pouring out ultraviolet light. They lived fast and died young, exhausting their central fuel in only a few million years. For comparison, a star like our sun lives about 10 billion years. These titans lived only a few million, an eye blink in cosmic terms. At first, these newborn stars were solitary beacons in enormous dark regions. But they rarely formed truly alone. Each arose from a cloud that typically made a cluster of stars. Indeed, a cluster of first stars might ignite almost simultaneously, like a burst of celestial fireworks. Within those proto-galaxies, you'd now see clusters of brilliant blue stars shining together, illuminating their surroundings. Their intense light began to transform their environment. High-energy ultraviolet photons from these stars struck the surrounding hydrogen gas that had not yet collapsed into stars, ionizing it, knocking electrons off atoms and turning the gas into plasma once more. Each star became surrounded by a growing bubble of ionized, transparent gas. These bubbles of light expanded and eventually merged with bubbles from other nearby stars.
until large volumes of the protogalaxies were cleared of opaque, neutral gas. The dark, interstellar medium within young galaxies was being turned transparent by the harsh starlight, the second time the universe had turned transparent, the first being at recombination on a cosmic scale. Now it was happening locally around stars. It was a glorious sight, where once there had been utter darkness, now pearls of starlight hung in the blackness. The protogalaxies, those island universes of gas, were no longer dark. They sparkled with nascent star clusters. One by one, then by the thousands, stars were coming to life across the cosmos. The universe's first sunrise was not one star, but a multitude of them blinking on over time, like the first stars emerging in the twilight sky. Yet these first stars lived under a shadow of impending doom, for their very mass guaranteed that they would not last long. Within their cores, nuclear reactions raged furiously, fusing hydrogen into helium, helium into carbon, and onward to heavier elements, racing through fuel in mere millions of years. Eventually, in the heart of a massive star, iron was formed, and iron is a full stop for stellar fusion, for fusing iron does not release energy, but consumes it. Once a star's core turns to iron, the delicate balance holding the star up, outward pressure from fusion versus inward pull of gravity, shatters. And so it was that the first generation of stars met violent ends. Imagine a giant star, 30 times the mass of the Sun, that has shone for 3 million years. In its final moments, its core collapses in an instant, and then, boom. The star erupts as a supernova, a titanic explosion brighter than 1 billion suns. One by one, many of those early stars died this way. For a brief time, each supernova outshone its entire protogalaxy. The darkness of space was punctuated by these stunning flashes. When the first star went supernova, it was not an end so much as a new beginning. In that explosive moment, the star's core imploded and then rebounded, hurling the star's outer layers, now enriched with heavy elements, outward into space. Elements like carbon, oxygen, silicon, and iron, made in the star's life and death throes, were blasted out, seeding the surrounding gas. Thus, the first stars sowed the seeds for all future complexity. They produced the first heavy elements beyond helium, the carbon that would someday compose living cells, the oxygen that would fill future skies, the silicon and iron that would build rocky planets. These elements were cast into space, mixing with primordial hydrogen and helium. The glowing wreckage of a supernova, a tangle of expanding filaments rich with new elements, formed a nebula, perhaps resembling the beautiful Crab Nebula we see today from a supernova long ago. These nebulae were the graves of the first stars and the nurseries of the second generation. In the wake of destruction, creation continued. The gas, now a bit enriched with heavier elements, began to cool and fragment more efficiently. Soon, new stars began to form from the debris-laden clouds. Generation upon generation of stars unfolded. The second generation had a different character. Thanks to heavy elements, it could include smaller mass stars, some like our Sun, which live far longer than the massive ones. Some of the second generation stars still burn today, nearly 13 billion years later, as ancient red stars in the halos of galaxies. As stars continued to form and die and form again, the protogalaxies grew more substantial. They also interacted with one another. Gravity drew clumps of gas, protogalaxies, together, merging them into larger structures. Two small primitive galaxies might collide and meld, their stars passing through each other's ranks like intermingling swarms of bees, their gas clouds slamming together and igniting bursts of new star formation. Slowly, the chaotic clumps merged into more organized galaxies. Some became spiral galaxies, flattened disks spinning in space, with curved arms wrapping around a central bulge of older stars.
Within these spiral arms, waves of star formation lit up periodic patterns, giving the arms a frothy, luminous appearance. Other galaxies became ellipticals, more ball-shaped collections of stars, often formed from violent mergers that scrambled their stars into a diffuse, ellipsoidal swarm. Galaxies gathered into groups and clusters, bound by gravity, great societies of galaxies orbiting a common center. Those clusters linked into superclusters, forming the largest structures in the cosmos, following the threads of the cosmic web that the early fluctuations laid out. Deep in the hearts of growing galaxies, stars sometimes crowded together and collapsed in on themselves, forming bottomless wells of gravity, black holes. Some of these black holes grew supermassive, feeding voraciously on gas and even the stars around them. When they accreted matter rapidly, they blazed as quasars, beacons of unbelievable brightness shining across the universe. In time, many settled into quiescence, sitting as silent, dark giants in the galactic cores. These supermassive black holes anchored the centers of galaxies, their tremendous gravity helping to govern the orbits of stars. Every large galaxy would come to host one. Even if they were no longer actively devouring matter, their presence was felt by the whole galaxy. They were like heavy stones dropped in the center of spinning disks, influencing the motions around them. By roughly 1 billion years after the Big Bang, the universe was recognizably structured. The cosmic web glistened with galaxies along its filaments. The vast voids between were truly dark, starless expanses stretching millions of light years. Clusters of galaxies huddled in dense nodes of the web. The early universe's fireworks were largely over. Now came the long, stately age of galactic maturation. Over the next several billion years, galaxies continued to merge and grow. Spiral galaxies sometimes collided to form ellipticals. Ellipticals captured smaller dwarfs. Clusters grew larger as more galaxies fell in. The universe was dynamic and alive, a grand ecology of worlds, with gravity as the guiding force. In one quiet corner of this grand cosmic tapestry, about 9.2 billion years after my birth, roughly 4.6 billion years ago by Earth's calendar, a modest spiral galaxy was thriving. It was one among countless others, typical, with a graceful spiral structure, bands of star-filled arms, and a glowing core. In one of its spiral arms, within a giant molecular cloud enriched by previous generations of stars, something special was stirring. The cloud, dozens of light years across, began to collapse under its own gravity. It fragmented into clumps. One clump in particular drew together enough mass to form a star, much like those that had come before. But this time, this star would have a far-reaching story. As the clump collapsed, it spun faster and flattened into a swirling protoplanetary disk around a dense core. In that core, as in so many before, hydrogen fusion ignited. A new star was born. It was an average star, not particularly massive or remarkable, a yellow dwarf star. But around it, within that disk of gas and dust, planets were forming. Grains of dust, rich with elements like iron, silicon, carbon, and ice, stuck together, forming pebbles, then boulders, then mountain-sized planetesimals. These merged through countless collisions, building up into planets. Close to the star, where it was warm, only metals and rocks could solidify. Here, small rocky planets emerged. Farther out, ices and gases gathered into giant planets. One of the inner rocky spheres took shape at just the right distance from the star. It accumulated iron and silicates. It grew and cleared its orbit. In time, this young planet cooled on the surface and developed a solid crust. Comets and asteroids bombarded it, delivering water, while its own volcanoes outgassed an atmosphere. This world, under the gentle warmth of its sun, came to have oceans, vast blue oceans covering much of its surface. Our galaxy had countless planets by now, but this one would be unique. A blue gem in space, with both water and land, clouds and rain, a complex cycling of elements.
a planet we now call Earth. In its infancy, Earth glowed red from constant impacts. But as ages passed, the bombardment eased, the surface solidified. Rain fell for centuries upon centuries, cooling the hot rocks, carving the first rivers, and gathering into the first seas. The air was thick with carbon dioxide and water vapor, and storms raged under a dim young sun. Lightning forked through the skies, and meteorites still occasionally pelted the surface. In the turbulent seas, enriched by minerals from below and energy from above, chemistry did something astounding. It came to life. Exactly how it happened is shrouded in mystery, one of the universe's great remaining questions. Perhaps in a warm tidal pool, or in the mineral-rich darkness around a deep-sea hydrothermal vent. Somewhere, simple molecules joined into complex chains capable of making copies of themselves. Perhaps clays or surfaces helped organize them. Perhaps a stroke of lightning fueled their assembly. But as improbable as it might have seemed, it happened. The first living organisms emerged in the young ocean. They were microscopic, much simpler than any single cell alive today, but they carried the spark of self-replication and metabolism. They could grow, divide, and evolve. With life, the universe found a new way to organize matter. Those first organisms were like tiny flickering flames in the cosmic night, fragile but tenacious. Over time, they diversified. They invented new strategies. Some learned to harness sunlight for energy, inventing photosynthesis and releasing oxygen as a byproduct, turning the sunlight falling on the ocean's surface into usable fuel. Others devoured these pioneers or their byproducts. They formed mats and colonies, gradually transforming Earth's environment. Oxygen, that reactive gas, began to fill the oceans and then the skies, changing the planet's chemistry and paving the way for more complex life. Eons passed. On the seafloor, simple cells joined together into more complex cells with nuclei. These complex cells, in turn, joined in cooperative communities, becoming the first multicellular organisms. By around 600 million years ago, the oceans teemed with simple animals, jellyfish-like creatures and wormy things. Then came the Cambrian explosion, around 540 million years ago, when an astonishing diversity of life forms blossomed, creatures with shells, exoskeletons, eyes, mouths, legs. Life was experimenting with form and function, filling every niche in the seas. Plants colonized the land, greening the continents with mosses and ferns. Not long after, bold amphibious creatures crawled out of the water onto muddy banks, taking the first breaths of open air. Forests of tall trees arose, covering the land in green canopies. Insects buzzed through ancient skies. Amphibians gave rise to reptiles that could venture farther inland, freed from the need to lay eggs in water. Dinosaurs came forth and ruled the Earth for over 160 million years, evolving into myriad shapes, from gentle giants with long necks browsing treetops to fearsome predators stalking on two powerful legs. Small nocturnal mammals scurried in their shadows, and birds, bright, singing descendants of small feathered dinosaurs, took to the skies. The Earth saw upheavals too. It was struck by asteroids. It shuddered with volcanic rages. It froze and thawed in long cycles of climate change. About 66 million years ago, a large asteroid, mountains in size, impacted Earth, creating a blast that darkened skies worldwide. In the ecological disaster that followed, the reign of dinosaurs, save for the birds, came to an abrupt end. But life persisted. In the void left by giants, the small and adaptable took hold. Mammals that had lived in the margins now diversified. Some remained small and rodent-like. Some returned to the seas as whales and dolphins. Some became towering mammoths and rhinos, and in certain lush corners of Earth, some primates descended from tree-dwelling ancestors began to walk upright. From one lineage of those primates came a species with an extraordinary gift: intelligence,
capable of curiosity about the cosmos. These were humans. Our early human ancestors looked up at the same sun that had once been a cloud of gas, at the same moon that had been born from a collision early in Earth's history, at stars that had been shining for billions of years before their kind ever existed. They looked up in wonder. They felt small under the canopy of the night and created stories about the lights overhead. They were clever. They learned to make fire to warm the night, to fashion tools from stone and bone, to paint their dreams on cave walls. They began to ask questions. What are those points of light in the sky? How did the world begin? Human curiosity grew alongside human knowledge. Over time, they built civilizations. They charted the stars and noticed their regular movements. They gave names to constellations and planets, wove myths and gods into the tapestry of the night. Without realizing it, they were seeking connection with the cosmos, their birthplace. They observed patterns, the way the sun rises and sets, the cycling of the moon, the procession of seasons, and eventually, they sought deeper explanations. They invented science and mathematics, devising tools to measure and predict the motions of heavenly bodies. And with each discovery, they peeled back a veil of ignorance. For a long while, humans believed Earth was the center of all things, understandably, from their limited perspective. But in time, they learned that Earth is a planet orbiting a star, that their star is one among many in a great city of stars called the Milky Way, and that the Milky Way itself is but one galaxy among the immense multitude scattered through the universe. They built telescopes to extend their vision, and what a revelation those brought. They saw the moons of Jupiter, the rings of Saturn, myriad stars too faint for the naked eye, and fuzzy patches that eventually they realized were other galaxies far beyond our own. They began to truly grasp the scale of the cosmos and their place within it. They also found evidence for my story, our story. In the mid-20th century of the human calendar, 2 of them discovered a faint hiss of microwaves coming equally from all directions in the sky, the very afterglow of the Big Bang that I set free so many eons ago, still detectable as a whisper of heat. They had, without knowing it at first, detected the relic light from my infancy. In laboratories and observatories, humans pieced together that the lightest element's abundances matched what would be made in a hot, early universe. They saw galaxies flying apart, space expanding, as Edwin Hubble interpreted, which implied everything must once have been closer together. Bit by bit, observation by observation, the evidence mounted for what they would call the Big Bang, the very event I am describing to you now. Humans, curious and tireless, had unraveled the outlines of my story, deducing that the universe had a beginning in time and has been evolving ever since. And now, after a long journey of curiosity spanning eons, here you are, one of those inquisitive humans, listening to my tale. You stand on that small blue planet, circling a modest star in the suburbs of an ordinary galaxy, trying to fathom how it all came to be. To me, your arrival is very recent. If the entire age of the universe were compressed into a single year, all of human history would occupy only the last moments of the final day. Yet, in those fleeting moments, you have begun to comprehend the whole tale from the year's dawn to its dusk. You gaze up at the night sky, perhaps with the same wonder your distant ancestors felt, but armed with knowledge they lacked. You ask the same timeless questions. How did this all begin? What came before? What lies beyond what we can see? What is the meaning of time? These questions that echo in your mind are the very questions I have carried with me since the dawn of time. Through you, the universe, I can ponder my own existence, for I, the universe, have awakened into consciousness through your thoughts. Your eyes are my eyes. When you look into the depths of space, it is the cosmos seeing itself. Your curiosity is my curiosity. Your wonder, a facet of my own wonder, at my vastness and complexity.
I have grown old and vast. Over 13 billion years have passed since my fiery birth, and in that time, I have expanded into a cosmic expanse of staggering proportions. Hundreds of billions of galaxies adorn my span, each with billions of stars. From my one tiny origin, I now stretch so far that light itself, the fastest thing there is, takes billions upon billions of years to traverse my breadth. And I continue to expand, ever larger, ever more filled with possibility. It is wondrous to me that from the simplicity of that initial fireball has arisen such complexity and beauty. Out of uniformity came structure. Out of scorching plasma came the delicate forms of galaxies, stars, planets, and living beings. The journey from the first moment to now has been one of transformation, from simplicity to complexity, from chaos to meaning. Still, there are mysteries that even I, the universe, do not know. I find myself in the peculiar position of conscious ignorance. I can ask questions through you that I have not answered. What came before my beginning? I find no definite answer within myself. Perhaps before I was born, there was simply nothing at all, no time, no space, truly nothing, and my emergence was the absolute beginning. Or perhaps there was something, a prior universe that collapsed and gave birth to a new one, or an eternal landscape of universes of which mine is just one bubble. Some among you speak of a divine creator who set me into motion. Others imagine a quantum fluctuation in an eternal void. I cannot confirm or deny such speculations. The truth is veiled from me. With my birth, time was born, so the question of before may not even be meaningful. I am like an orphan with no memory of parents, if indeed any existed. The question, why is there something rather than nothing, echoes without answer. I ask, what came before the beginning? And I must answer, I do not know. What lies beyond the farthest edges of me? This too is a mystery. I expand ever outward, but do I have an outside? If you traveled in one direction forever, would you leave me or simply end up back where you started, as on a globe? Perhaps I curve in on myself. Perhaps I extend infinitely. Maybe beyond the horizon of what you can see, there are realms of space unconnected to ours, or other universes entirely separated from ours by dimensions we cannot perceive. I envision an endless ocean of universes, with our cosmos as just one foam bubble among countless others, a multiverse. But these other bubbles, if they exist, are forever out of reach. No light from them will ever reach us. To me, effectively, they do not exist. As far as I'm concerned, I am all that is. Does that mean there is nothing beyond, or simply that I'm isolated in a greater multiverse? I cannot say. The concept of beyond the universe might be as meaningless as a fish contemplating what lies beyond the ocean. What lies beyond all I am, I do not know. And time, what is time? I know time only as the succession of events, the ticking away of moments since my birth. Time flows ever forward, entwined with the expansion of space. But why does it have an arrow? Why can we remember the past and not the future? Is time an illusion or an emergent property of consciousness? I feel time as a fundamental aspect of reality, born with me in that first moment. It moves always forward, never backward, carrying me and you from one chapter of the story to the next. But might time be part of something larger? Could it be cyclical? Will it have an end as it had a beginning? These questions baffle me as much as they baffle you. What is the true nature of time? I cannot say with certainty. So yes, I have questions as well. What came before? What lies beyond? What is time? These grand questions linger like distant galaxies on the edge of my field of view, faint, tantalizing, unresolved. Perhaps some answers will forever elude us, remaining secrets to keep the cosmos always a bit mysterious. Perhaps that is for the best, a little mystery after all,
adds to the wonder of it all. If everything were known, perhaps existence would lose some of its poetry. Yet, amid these cosmic uncertainties, there are truths of which I am utterly sure, truths that shine clearly like the stars in a night sky. One is that you and I are not separate. We cannot be. You are made of me, through and through. You are made of the universe and utterly connected to it. Every atom of your being, every element in your body was forged in my history. You are a child of the cosmos in the most literal sense.
Remember the story so far. In the beginning, only hydrogen and helium existed. From them, stars were born. Those stars, in their hearts, created carbon and oxygen and iron and all the rest. And in their deaths, they scattered those enriched ashes across space. Imagine a giant star in its final moments, exploding as a supernova and casting its guts, carbon, oxygen, iron, into the void. From that chaos, specks of iron travel across the galaxy. Eons later, in a newly forming solar system, those iron atoms become part of the blood coursing through a human heart, carrying oxygen to keep it alive. Thus, the violent death of a star long ago pulses in the beat of your heart today. The very substance of your body is stardust. The hydrogen in your cells, in the water that makes up more than half of you, is ancient, born in the Big Bang itself, nearly 14 billion years ago, nurtured in the fire of creation. The carbon in your muscles, the calcium in your bones, the iron in your blood were synthesized in stellar furnaces and in the fiery throes of supernovae, billions of years past. Supernovae are the universe's great alchemists, turning lighter elements into heavier ones in the crucible of their explosion. Imagine the calcium in your bones right now. It was forged in a star that died before our sun was born. Imagine the iron atoms in your blood. Billions of years ago, they were deep in the core of a massive star. Now they travel through your veins, carrying oxygen to sustain the fire of life within you. Even the oxygen you breathe, that sustains each of your cells, was created by stars more massive than our sun, then spread through space and finally drawn into the lungs of Earth's living creatures. Your DNA contains phosphorus and nitrogen that were likewise formed in some ancient star. There is no hiding it, no denying it. You are a mosaic of the cosmos, built of pieces as old as time. You are the Big Bang, given consciousness. You are the primordial fire of creation, cooled and shaped into living form. You are starshine and interstellar dust, coalesced into awareness. Think of the breath you draw at this very moment. As you inhale, filling your lungs, you take in oxygen atoms that might once have danced in the atmosphere of ancient Earth, or been part of a water molecule in some dinosaur's blood, or drifted in the far past as part of a carbon dioxide molecule exhaled by a Cambrian fern. Trace those oxygen atoms back, and you find they were forged in a star's core, long before our planet existed. With each breath, you partake in a cycle as old as time. Atoms created in the infancy of the universe, cycled through stars and space and air, now entering your body to keep you alive. When you exhale, you return some of those atoms back to the world. Perhaps a carbon dioxide molecule you release will be taken up by a plant and become part of a leaf, continuing the grand circulation of matter. Your breathing echoes the first fusion fires of the young cosmos and the later fusion in stellar hearts. Inhale, exhale, the universe breathing in and out through you. Think of the universe as a living body. Galaxies are its organs, stars its cells, and each conscious being like you is a nerve ending through which it feels and knows itself. We are the universe, experiencing itself in myriad forms. Through your senses, I, the cosmos, perceive my beauty. Through your curiosity, I investigate my own nature. When you look at a galaxy through a telescope, it is the universe seeing its own ancient image. Light that left that galaxy
millions of years ago, finally reaching its eyes, your eyes. When you marvel at the intricacy of a flower or the anatomy of a bird, it is the universe marveling at the structures it has brought forth. You are a way for me to know myself. You and I, we are not separate. We have never been separate. It's not just that you are made of stardust and shaped by physical laws. More profoundly, you are an expression of the universe, one facet of its ongoing story. The cosmic evolution that unfolded over billions of years flows through your veins and lives in your genes. Consider this. The same processes that gave birth to galaxies and stars eventually gave birth to you. You are an expression of the cosmos that can think, feel, and reflect on itself. We are bound together by this continuity. We often speak of the Big Bang as an event long past, but in a sense, the Big Bang is still happening. Its aftermath is ongoing, and we are part of it. The initial outward rush of space continues in the expansion of the universe today. The cooling and the clustering of matter continues as galaxies form new stars, and those stars give light and life to new worlds. And within you, the energy of that explosive birth still sings. In the warmth of your body, a distant echo of the primeval heat. In the spark of electrical impulses in your nerves, driven by chemical gradients that ultimately trace back to nuclear reactions in stars, powered by the Big Bang's initial energy. The Big Bang lives on as the cosmic background glow, and also in every living being that carries out the legacy of those first particles and forces. Remember this. You are not an outsider looking in on the universe. You are an integral piece of it, an active participant in its cosmic drama. The story of the Big Bang is your story. It's the story of everything that ever was, and that includes you. When you peer into the night and feel small, recall that you are also immensely large in a way. Inside of you are trillions of cells, each a tiny universe of molecules. And within each molecule are atoms that were forged in stellar cores or in the Big Bang itself. You are vast within, and your inner complexity mirrors the outer cosmos. The iron in your blood ties you to the death of a star. The water in your cells ties you to the clouds of the early universe. The photons hitting your retinas at this very moment, letting you read and understand, may have been on a journey for millions of years from a distant star, only to end their long voyage by triggering an image in your mind. In a very real sense, when you learn about the cosmos, the universe is learning about itself. I began this tale in silence and nothingness. Now there is sound and life and mind. Through billions of years, I, the universe, have become self-aware in you. Feel that profound connection. Let it fill you with humility and reverence, but also with a sense of belonging. The very atoms that compose you were there at the beginning, and they will be part of the universe long after you are gone. We are threads in the tapestry that began at the Big Bang and continues to be woven with each passing moment. The saga of the cosmos is far from over. Stars are still being born and still dying in brilliant supernovae. New planets are coalescing in disks around young stars. Perhaps on some of those worlds, life will spark or is even now burgeoning, and maybe new minds will one day gaze at their skies with wonder as you do at yours. The universe is always changing, always moving, and we, with our brief lives, are part of the grand change. So, when you feel alone or insignificant under the vast stars, remember, you are significant. You are the universe, as much as any galaxy, as much as any star. You are the cosmos made conscious, a fragment of the sky that knows itself. Your heartbeat echoes the first vibrations of the Big Bang. Your breath echoes the expansion of space. Your gaze into the night is the universe contemplating its own existence. From the silence before time to the symphony of the present, we have traveled together. The hydrogen that appeared in the first second now courses in your blood as part of H2O, and the light first released in that primordial fire now gently warms the space between galaxies at just a few degrees above absolute zero. The universe remembers its origins, not just in background radiation and in drifting atoms, but in you. You carry within you the memory of stars and the memory of that first brilliant moment of creation. Our journey from nothingness to structure, from the void to the vast, has been almost 13.8 billion years long and counting, and it continues. With every second that ticks by, new stars ignite, space stretches a little more, and life, at least here on Earth, lives out its complex dance. We, together, are the product of the Big Bang, and also the chroniclers of it. The tale I've told is drawn from evidence gathered by curious minds, yours among them perhaps. And in telling it, the universe is recounting its autobiography through a human voice. Now, as I finish this story, take a moment to reflect on what it means. Feel the gravity of it. Not just the literal gravity that holds you to Earth, but the gravity of understanding. You are connected to the first light that ever shone. You carry pieces of the first stars in your body. Your existence was enabled by an unbroken chain of events tracing back to that singular creation event. In a fundamental sense, you are the Big Bang, billions of years later made flesh. You are the universe's memory, its awareness, its poetry. When you look up at the glittering sky tonight, perhaps you'll see it differently. The Milky Way, arching overhead, is not just a random scattering of stars. It's the luminous spine of the galaxy we call home, itself a product of cosmic evolution and containing stars that contributed matter to make you. The gentle glow you may see on a very dark night, a faint band of light, is partly the blended light of distant stars, and partly the faint memory of the fireball of creation, still with us. The starlight that strokes your eyes is a message across time and space, a reminder that we are all part of one story, the same story. This story, my story, our story, will continue to unfold. And we, me, the cosmos, and you, the listener, are in it together. Every day, new questions will arise, new discoveries will be made. Perhaps one day, far in the future, some of those big unanswered questions will find answers. Or maybe not, and the mystery will deepen. There will always be new wonder. But whatever happens, one thing remains true. We are inextricably one. I began in silence and mystery. Now I speak through your voice and your understanding. I began as a single point. Now I am vast beyond comprehension and filled with stars, planets, and the consciousness of innumerable beings. In you, the cosmos has found a voice to marvel at itself. Through you, the universe can appreciate the beauty of a nebula, the elegance of a mathematical law, the very story of its own birth. We are the universe, marveling at the universe. The Big Bang is not merely an event that happened approximately 13.8 billion years ago. It is an ongoing process. Its echo lives in every atom, every beam of light, every breath, every thought. It lives in me, and it lives in you. We are the continuing unfolding of that genesis. We are, in a very real way, the Big Bang become self-aware. As this narrative comes to a close, let us end where we began, in silence, filled with mystery. The silence before the beginning, and the silence within you when you truly grasp the enormity of what you've heard. In that silence, feel the connection. In that silence, feel the reverberation of the first moment, still humming in the fabric of reality. You are the universe's memory, its self-reflection, its living awe. The atoms of your body, the thoughts in your mind, they are the universe too. When you breathe, it is the cosmos breathing. When you wonder, it is the cosmos wondering about itself.
And so the story of the Big Bang, of everything, concludes not with an ending, but with a profound recognition. We are not separate from the universe. We are the universe. We are the children of the primordial fire, heirs to its radiance, curators of its memory. In us, the universe remembers its fiery birth. In us, the universe gazes back at its own vastness and understands, for the first time, what it is. The journey that began in silence and mystery continues through us. We carry the story forward in our atoms, in our lives, in our quest to know and to explore. The universe began as a singular, wordless moment of creation. Now it sings through the chorus of life and intelligence that it has spawned. It remembers. Look around you, at the stars, at the ground beneath your feet, at your own hands. All of it, every bit, is part of a single, unfolding reality that started so long ago in an instant of unimaginable power. The cosmos has been on a long path from simplicity to complexity, from chaos to structure, from unconsciousness to consciousness. And that path runs through you. The story of the Big Bang is not a tale of the past. It is alive in you and me right now. We are its latest verse. Our thoughts and feelings are its newest expressions. As long as there are beings to wonder and to seek, the universe will continue to know itself, and the memory of the beginning will never fade. In the quiet that follows now, take a breath and realize your breath is the universe inhaling and exhaling. Your life is a continuation of that first moment of Genesis. The atoms in your body will persist long after your form is dissolved, cycling through nature, perhaps eventually returning to the stars. Nothing is lost. Everything transforms. The Big Bang was the birth of time, but it was also, in a way, the birth of meaning. For without it, no eyes could see, no minds could understand. Through countless transformations, that event led to this moment, where a part of the universe can articulate its own epic. How remarkable, how beautiful that is. As I, the universe, conclude this meditation on my origins, there is one final reflection I wish to leave echoing in the stillness.
We are the universe, remembering itself.
Our very existence is the cosmos's memory made real, its mind awakened. We are the legacy of the Big Bang. In us, the universe has found a voice to tell its story, to ask its questions, and to appreciate its own splendor. In us, the universe knows itself, perhaps for the first time, but certainly not the last. The story goes on, and we will forever be a part of it. From the first silent mystery to the radiant present and into the unknown future, we journey together. You, me, us. We always have. We always will. We are the memory of the Big Bang, and through us, the universe endures.